decoders, or also the type of like memory windows which can be shared with this through these structures. So the CDT CHBA structure would share the pointer where the host bridge registers can be configured for any sort of HDM decoders uh, configuration required based on the topology. Yeah, and 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 it there should be unique ACPI objects. I mean, for each host bridge, there should be an associated CSBS, and the UID object under the host bridge object should match with the UID of the CHBA structure. So that's how they form the relation, and it picks up in the topology. And the fixed memory window structure, and that would define a memory ranges available in the host system, which can be mapped for accessing the device remote device memory ranges. And if there is multiple targets for a host for a memory range, which can be also described in this structure, and whatever the interleaving ways being configured, so all those properties and details can be mentioned in the structure, where kernel can pick up the details and do necessary configurations. So these are the tables what's being prepared in the firmware in the EDK2, and shared with the kernel for the kernel CXL framework to consume and mm, prepare the right topologies and do the right configuration. Into the uh, hardware platform. So uh, the fixed virtual platform is the test platform for this work, and it's the a little background about this FVP. It's a complete simulation of an ARM system. It includes processor, interconnects, and memory, and some of the peripherals also. And it gives a lot of flexibility in customizing the model. For current work, the RD newest N2 FVP model is chosen, and and the CXL support is being added into this. So which is not yet complete. It is evolving actually. So some of the features which have been added are like DVSec registers, mailbox, CDAT, DOE capabilities, and HDM interleaving logic is not fully yet completed. So, but it's ongoing task. So, so in a sense, this FVP model gives a lot of flexibility in designing and customizing according to the need. And why FVP is like in the absence of the real hardware, it allows the software uh, community and the developers to prepare the framework where it can where they can verify the functionality. It for functional verification, it's a well suited model. It is fast. Yes, in case if there is a need of uh, where there is a time accuracy or the performance tuning kind of requirement, then this platform is not suitable. But for our CXL framework firmware development, it's well suited. So and we can keep adding the features of the CXL as well, and keep uh, evolving both in the AVP as well as in the framework in the software side. So and then it also allows the user to debug. It comes along with a lot of libraries and tools, so there can be a lot of way to debug also what kind of data transactions are being happening, and yeah, things like that. uh, this is very high level presentations of this into SOC. What exactly are there, just to give what kind of hardware we are using, and how exactly is the communication is being happening. And so into we have the SCP block, which is the system control processor. It has a M7 core in it, and it would control the whole system's power reset clock domains. And so in a sense it's kind of a master. And there is this application processor block, uh, which would be having ARM v9 node based cores. And TMN 700 is the main interconnect, in this talk, which will be having different nodes in it for connecting all the blocks around. And IO virtualization block, which has a multiple lanes under it, and there can be multiple root ports being can be connected. Root devices can be connected in the downstream port of this IO virtualization block, and that's what being utilized. And in 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 this development work, there is a CXL capable root device has been plugged in here under one of these IO virtualization block. And there is one CXL type 3 device capable of certain properties which are highlighted here. So that's been placed under this root device. And and that's how this CXL IO communication happens through this block. And for the remote memory range, so a portion of system memory has been chosen, and it's considered as a remote memory, and that range is being configured in the CCG port. So the CCG port is the CMN 700 port for doing the CXL MEM transactions. So it is CXL 2.0 compatible, and that's what is being configured for accessing performing any kind of CXL MEM transactions. And this so HDM memory, what's highlighted here, it would be remote memory and considered as a CXL mem, and the DRAM is the local memory. So that's how we're trying to uh, demonstrate a memory expansion capability using the CXL framework. And so one thing to mention here is the FBP allows just by modifying some script logic to have multiple CXL devices under this root port, and that sort of topology can be uh, just on the fly can be done. Yeah. Coming to the firmware work, so we start with the system control processor where the actual boot process starts. And first thing for this work is being done is the interconnect configuration so that PCIe enumeration can happen, and CXL device uh, with the extended capability of the CXL and DOE capability is found. If found, then the its CDAT tables are read out, and what all properties, and basically it just tries to find out the device, the kind of memory ranges it supports. So once that memory range is found, so it needs to configure, once the memory range is being found, it needs to configure the interconnect for doing this any sort of MEM configuration. So that's the sole purpose, and it's being done before AP boot. So that's why this enumeration and doing DOE operations and understanding the kind of range it supports, and and configure the interconnect accordingly. So that's what being done in the firmware in the system control processor, and in the subsequently when the boot phase comes into EDK2, uh, and in the EDK2's PCI enumeration phase, it has already. So when it kicks in, it will also during the enumeration process, it will also invoke the CXL Dixie, which is newly introduced. So it will invoke CXL Dixie routines to also find out a PCI device with extended capability of the CXL and DOE, and if again in there also if it is found, so then the CDAT like DS mass and DSE MTS tables should be fetched out to understand the kind of memory ranges and what kind of memory and what kind of EFI memory types it supports, and so those details would be captured and kept in a local data structure for later platform driver to use. And when the execution reaches platform Dixie, so and then when it tries to prepare these SRAT, HMAT tables, SPA tables, so it would fetch, it would invoke those CXL Dixie protocol routine interfaces, and fetch those details and prepare necessary uh, all the ACPI structures, and that's how all the ACPI structures should be prepared, and also the structures for the CDTs and CXL root device would be prepared and shared with kernel during the boot process in the next phase of the boot. When the kernel comes, it would pick up all those ACPI tables. And in kernel already there is a framework to understand those ACPI tables and pick up the details and do the configurations and uh, prepare the topology, right topology. So in kernel, for now, we are just utilizing, which is well covered CXL framework, and and seeing that validating the firmware is rightly done or not, whether it's preparing the tables properly or not. So the firmware is not only here helped us in validating this firmware work. The kernel not only validate helped us in validating this firmware work, it also helped us like in understanding how exactly it should be done in the firmware, and what kind of data should be populated in the ACPI tables, and what's the right topology to keep there. So that way it was uh, good for us to understand the framework and utilize it. And for memory nodes, it's just uses the NUMA framework. So the educative work has been published recently for RFC, and the links are shared here. Uh, Please have a look if when you get time, and share your feedback. We'd be happy to address that and rework accordingly. Yeah. And this is just a presentation of like what's the kind of topology is currently done, and what's so so we have a single endpoint. Yeah, there are multiple endpoints, but for CXL, there is a CXL capable single endpoint, single root port, single host bridge. Uh, just utilizing the software framework and uh, in model, the FVP model, what we are using right now, don't have the interleaving logic completely. So we're just using it in the framework to populate the data structures properly. And so when we publish these the memory window structures, it is just one way, one decoder configurations, and it's a one way or almost one way or non interleaving configurations. But the AVP allow has the flexibility to add another endpoint in this topology just by modifying the script at runtime. So uh, it can be done, and tables can be modified. Table configurations can be modified accordingly, just to your trying to make the interleaving logic work here, so that it keeps more value addition in this all solution. Yeah. On the status and current completed and what's the next task we are aiming for. Currently we have the CXL device enumerations and all the ACPA table preparations. Uh, those things are done at 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 the current stage. What the kind of AVP supports at that extent, but definitely it would be evolving. And there will be more contents would be added, and more intricacies will be added in these tables and the data configurations. And now on the future side, next thing, one thing first thing we would like to have is like the complete interleaving capability in the AVP, and software also would be enhanced to demonstrate that complete capability. And yeah, of course, would be uh, will continue engagement with the developer community, and contribute to whatever possible way in the firmware and the kernel. And from the architectural point of view, memory pooling is one of the topic which is the next uh, next topic, next in the next architecture, which is being investigated. So we'll work on it and come to it when there is more things, more substantial things in picture. Yeah. And and then and another thing we definitely want to cover is like this SBBR, which is server-based boot requirements. So many of the points in the SBBR are covered with this development, like preparing ACPI tables and considering the memory types and attributes. Uh, so many things are covered considering this memory expansion use case. But there are many, as we add more features, there will be more points to cover. So we definitely would like to have that coverage as much as we can to make the solution more standard and acceptable in community as well. And yeah, from kernel point of view, we'll continue using the latest kernel and also validating the firmware. And also, in a sense, if there is any contribution from our side, we'll try to do that. And on the reference side, these are the couple of references we are sharing. So the first is the link for where the Neoverse reference solution is being published. So it would give a sense of like what kind of support is there and with some details. So it may help for the developers. And for the FVP download link, that FVP is downloadable for everyone. So anyone can download and try any try any kind of experiments they want to do. So yeah, that would be all from my side for now. Yeah, thanks for attending. If there is any
One
question, we can, yeah.
one question, and you have mentioned that the memory, the 6 memory is treated as NUMA node, and I see that in the previous slides. Yeah, and the next you have seen in the future work, you will deal with the memory pooling. So how we deal with the 6 memory? I mean, because I don't think it's belong to the NUMA. Uh,
Right,
belong
right.
to
I get your point. Yeah. So that's kind of a topic which is still under a bit of debate, and I don't think there is a very conclusive answer to that yet. So that's why it's still under investigation. Yes, of course, the NUMA it can't be that's not so efficient the that protocol, and considering pool memory that may not be the right way to use it. So how that far memory or the near memory would be managed, still it's being discussed. And yeah, so I don't have clear answer to that yet. Maybe the in near future would be in a better position to answer that. Yeah.
um uh so now for example in our system we have the high bandwidth memory. It's very fast DRAM, and
Yes.
and we have the 6 memory, and we put them in the same memory address range, and it doesn't mean some address range would be slower than others.
Right.
um, is there any proposal or patch related to this work? Because when we introduce the 6 memory into this kernel, we must deal with it. It looks like a cache hierarchy, but it's not a cache hierarchy. It's
Guys, guys, can I just ask you to stop a minute? We need to switch the on-site room to microphone mode so they can talk to you as well.
okay.
Sorry, can you repeat the last part of your question?
Um, uh, my uh, my last question is uh, my last question is how we when we introduce the 6 memory into the this kernel, we will make a different range of different speed of the memory. Some address range behave faster, such as the high bandwidth memory, and some would be belong to the 6L memory, and and it looks like a cache hierarchy. I mean, different speed, but they are memory. They are the memory range of that.
Yes, yes, that's true. When you have a CXL memory, that share different properties, and that may have different properties and attributes, and that may share different bandwidth attributes. That's where it's being tried to be captured in some of the ACPI in the HMAT and all those nodes. But that's not enough. There are certain uh, algorithms or things need to be there for like uh, for efficiently managing this and then distinguishing this remote memory and the local memory. Uh, but yeah, that's a bit of out of scope from our work right now, and so maybe yeah. So maybe in near future when we go in further testings and things like that, so maybe we'll be in a we'll have more clear
Let's
answer to
wrap it
that.
up
Yeah.
for the next speaker too. And I don't know. Maybe later. I think maybe Dan want to jump in on this. I don't know if you quickly want to say something, Dan.
Oh no, I was going to ask a naive question about like is this code going into the EDK2 stream and can QEMU take advantage of it? But yeah, we can take that offline. But yeah. But I think we're gonna talk later about memory pooling and things, right? So I think we'll circle back to some of these questions in later sessions.
All right.
Okay.
Let's thank the
Sure.
speaker and.
Yep. Thank you. Thanks, Adrian.
Break the microphone. I'm going to be co-presenting with Navneet, who's online. So you may hear a few instances of next slide, please, later in this set. So what we're going to talk about here is kind of on the basis that CXL2 is basically solved. I mean, there's not really any problems. The rest of the talks today on that stuff, it's fine. Let's move on to the new stuff. So this talk is going to be all about things that are in CXL3, which has been out for, what, a month? Something like that. So yeah, we had fun writing the abstract for this one because we couldn't actually talk about the content. But now we can. So it's all about the stuff that's just been mentioned, memory pooling and the features that come in CXL3 that make this a bit easier. You can do it in CXL2, but there's an awful lot of basically hot plug-in whole devices to enable it if you're doing it in CXL2 because you don't have the ability to resize things easily. So what are we actually after from this session? It's Plumbers. We don't just want to present a set of slides. We want some feedback. There is an element of this presentation where I would say the main aim is actually to scare people and say there's some really nasty stuff that has implications in quite a lot of memory management code, DAX. I'm sure Dan will chip in on some of that. And it's not obvious what the answer is. It's going to take us a while, but hey, the spec's only been out for a month. We've got a bit of time. So we obviously want some discussion. So just, yeah, anyone in the room or online, just jump right in. I can't even see if anyone puts their hand up. I'll rely on someone telling me if they do. It's unlikely we'll get to any conclusions today. There isn't any code. There's the very first outlines of some emulation, but no more than that. It may well be, actually, and that was the question I was going to ask in the previous talk, there might be something coming in that ARM FVP that will give us a good platform for some of this. So there's also a broad strategy question that will come up in this, which is that we have a number of features, some of which are reasonably lightweight to implement. They're not particularly nasty, and some of which are very nasty, that add a lot of extra complexities. And the problem we have is that if we try and solve the simple ones first, we may well end up with an architecture that's just not extensible to take the complex ones in. And the question then becomes, do we actually care? I mean, it's not necessarily a problem if we have to do something different when it gets tricky. So, quick overview. As ever, to Plumbers Talk, nowhere near enough time. So we'll be going quick for some of this. We're going to give my co-presenter online, Navneet, is going to give an introduction to DCD in general, which is dynamic capacity devices. We'll have a little tiny bit on use cases, but if you're actually interested in this stuff, there are various papers that have come out now that talk about uses for memory pooling. We're just going to touch on it to give us a bit of motivation to the rest. Then we're going to get to the fun topic, which is memory sharing. We'll come back to that later. Hopefully we'll have time. And then, yeah, okay, plan is probably too much of a description. The screens? Let's come back. Okay, so Navneet, over to you.
Thanks, Jonathan. Hello, everyone. This is Navneet here from Intel. I'm basically working on the memory pooling solution. Today, I'm going to talk about I'm going to give basic DCD overview and also going to touch a bit upon the use cases of it. So let's start with the DCD overview. CXL 3.0 introduces dynamic capacity device. It's a CXL memory device which allows device memory capacity to change without resetting it. Each dynamic capacity device can have 1 to 8 DCD region. Each DCD region is basically divided into fixed size blocks. And these are the blocks used to allocate to the host. And at boot, the host software is responsible for querying the dynamic capacity region, the capacity, and to map it to the host physical address, which is provided by CDT, CXL fixed window memory structure in CDT ACPI table. During boot, once this is mapped using one or more SDM decoders, and during boot, there's no extent presence. Extents are basically a continuous region which consists of the dynamic capacity block base address and the size. And extents are used to allocate and release memory to the host. So hosts are informed using the extents what memory region they are allowed to access. And once they are done, or they want to release the memory, they can release some of the memories using the extents. Next slide, please. Okay. So whenever there's a okay, so whenever the host is under pressure or a host need more memory, it can talk to the out-of-band agent to add some of the memory extents. It can talk to the CXL device. CXL device can allocate some of the DCD memory blocks. It can create some extent. When extents are created, it can inform, or it can raise the event to the device. The device driver can handle this event via, it can handle this event, or it can handle the interrupt provided by the or raised by the CXL device. And it will pass the, it will get the event log, it will get the events out of the event log, and event extent consists of the DPA. It will translate the DPA into the HPA, and it will provision that memory to the host by different means. It can be behind the text device, or it can give that memory to the CXL memory manager, which can map it to the system address space. So once a block is created, driver has consumed the extent, it can notify back to the device what memory has been consumed, and it can also create an extent and give it back to the device so that device can update the existing extent. So TCD basically creates or maintains one extent list per host, and it can basically provide different DPA ranges to different devices, to different hosts. Next slide, please. In this slide, DCD is going to provide, DCD is providing more extents to the host in the red blocks in the same manner as before. And once this is more extents are provided to the host, the extent list are updated for that particular host. Next slide. Driver can be notified for the release of the extent in the similar fashion to the adding of the memory, right? In that case, an extent can be created and sent to the host, informed via the interrupt. Driver can find out what are the extents or what are the DPA base and sizes are requested to be released. It's a scary force because some of the pages can be pinned by the kernel and can't release that memory synchronously, or it may release the memory a chunk in the chunks in an asynchronous manner. In that case, driver can inform the Linux kernel memory manager to not to use this memory because we are going to release this memory back to the device. Next line. Yeah. So if Linux can release the extent, it can stop using it, and it can asynchronously call the mailbox commands like release capacity, dynamic capacity, and provides the extent what are the DP and the sizes has been released, and so that dynamic device DCD can update its extent list maintained for that particular host. And next. So here we have covered some of the high-level use cases of the DCD. So, as discussed previous also, DCD can enable memory pooling. It can provide really lightweight of memory hot plug sort of feature, right? So let's say if there is some app workload which is running on a host and it temporarily need more memory due to spike, right? DCD can provide that memory from the pool, and which can lead to the which can help us to reduce the TCO of that, right? Dynamic aspects brings repurpose of the memory. So same memory can be provisioned to multiple hosts. Classic example is if there are multiple hosts and we need to do the software upgrade or the database upgrade of all the hosts in a round robin fashion, then each host can use the same memory in a round robin fashion, and instead of over provisioning the memory. Next slide, please. Yeah, so DCD can also help in make use of the idle compute by provisioning the memory from the pool using the DCD. So let's say we have a server. In this server, there is some workload running and which has exhausted the local memory completely, and we still have some of the compute left. So with the DCD, we can provision memory from the pool to the new application, and once this application is done, we can release the whole memory back to the pool, right? And memory sharing, it basically enables the memory sharing among compute hosts. So as mentioned, DCD basically maintains a separate extent list per host, and it can assign different DPA ranges to different hosts. And it also provides some of the sequence numbers and to take care of them, to handle the memory sharing among multiple compute hosts. Yeah, that's all about the use cases and the brief introduction of the DCD. Over to you, Jonathan.
Okay, before we move on, have we got any questions about the sort of basic concepts of what DCD is? Anything about that? Someone want to provide? Get a microphone. Sorry. I was going to say one-handed is optimistic. He was holding a laptop in the other hand, if you can't see him.
I just have a quick. I'm probably not thinking about this right away, but when I read memory sharing among compute hosts, that kind of reminds me of old concepts like swapping over TCP. Is this like that? Not, it's obviously completely different, but is that kind of like where we're going?
No, not really. I mean, yeah, the concept of memory pooling absolutely could be used in some of those environments. I would postpone detailed sharing discussion because we haven't really introduced it yet, and there is a bit on it a bit later. So I don't know if Jerome's going for that. But we wanted to just start with the non-sharing case more or less, but just mention it was there.
My next question was like, with this pool of memory, what's like, how are we going to ensure that we're not actually like wasting memory in a pool?
Effectively the same problem as wasting memory anywhere.
But we don't have a pool, that's why like.
Yes. I mean, the nature of it is you've pushed some of this stuff out to what is effectively an appliance. I mean, the memory pool devices are typically a box at the top of your rack with an awful lot of memory in it. It can do an awful lot of monitoring in theory. In practice, much like some of the earlier discussions we've had during Plumbers on hot page tracking, cold page tracking, any understanding of memory usage, there's a whole load of questions around what hardware do we need? How do we actually go about monitoring this? And at the moment, there isn't really an answer. Absolutely, some of the software techniques that have been referred to during various other talks will work fine. It's just memory. And there certainly are use cases, particularly when, so there's I can't remember whose paper it was. There's a paper on memory pooling usage. Was it Meta? Someone put one out that basically talked about this case of stranded compute and the savings they could get. And I think they were doing it on a fairly static basis because it was a question of they knew what VMs they were loading, what the working set size was.
Yeah.
The more dynamic case is tricky, but we do have the tools to do something about it if we know the answer, because we can scale things up and down very dynamically, which is a bit more, I mean, it's a bit like the virtualization case of VirtuoMem, where you can poke little tiny bits of extra memory into VMs if they need it. And you have very good sort of granularity of control, but you've still got the question of how do you know what to do?
Question about the, so I see the problem as unplug. It's an unplug problem, right? And we have good ways of getting at that now, like with like DAX KMEM, and then like, well, attempting to work on the problem. I guess all I'm saying is like the whole start simple approach, right? I think we just got to get better at unplug in the beginning, right? And build upon that for anything else here. I think, is that the question about
the unplug thing? Absolutely. So I'm trying to remember what we actually have on the slides on this. I think we have some material, amazingly enough, on DAX and how it applies to this. So we'll move on and hopefully we'll answer the sort of question as we go along. Yeah, as mentioned here, dynamic capacity devices, as summarized, do have the ability to allocate new physical capacity to a host and, as you mentioned, request it back again. Now, the get it back again thing's always been a bit of a problem because hot remove of normal RAM, you've got all of the usual problems of there's something pinned in it. There is masses of work going on to enable ways of improving that. And hopefully we can take full advantage of that if we're treating it as normal memory. Now, the other option is what we've done for most CXL memory that hasn't been handled by the firmware and hasn't been set up already, is that the sort of standard approach of the kernel is to treat it as, from ACPI point of view, specific purpose memory, which means that we're shoving it into DAX by default. We have the option of KMEM. If you use KMEM, then stuff might get pinned and bad luck, you can't have it back. The one key thing on the dynamic capacity stuff is, in most cases, the OS and the host is allowed to say, no, you can't have that memory back. I know you want it, but no. And that does give us some flexibility. Now, obviously, this doesn't scale perfectly because you get the host that's crashed. You need to recover it. So there is a forced path. And from a software point of view, that probably means going out and killing software and possibly panicking the machine, depending on exactly what memory you're being forced to remove. It's the same problem that occurred with traditional hot plug and indeed hot plug into virtual machines. DAX makes this easier. There are some sort of mapping questions of how we map it to DAX. So DAX already has a concept of regions. You can have multiple carved out chunks of memory within a given DAX device. Yep, we do need to add some stuff. It doesn't really, well, as far as I know, it doesn't have a concept of sparse memory. It doesn't have this idea that the physical addresses are not all continuous. You've got gaps punched in there. Those gaps are going to change because you'll get releases for chunks of memory in the middle of your range. So we will need some new infrastructure to deal with that.
I have a question. This is music to my ears, if I'm understanding it correctly. From the point of virtualization, I could potentially live migrate a VM from host memory into this NUMA node, and then potentially pick it up on another host out of that NUMA.
Again, let's leave, because that would be, okay, that's not technically a sharing problem. So yeah, okay, yes, let's discuss it now. Absolutely, you can indeed do those sort of transfers. There are security issues around it, so you have to very much have your orchestrator opt in. So when it issues the commands to the Fabric Manager, there's a whole API for controlling the device. It has to say, normally it would assume it needs to wipe it because it's passing memory to a different host. But yeah, you absolutely have the potential just to hand it over. You'll need to be a little bit careful because, as was touched on by Navneet earlier, there isn't actually a guarantee that you would present the underlying physical memory at a memory address range that would then map onto the new machine. But again, if you're doing it for memory in a VM, you've probably got the option in a what would be a stage 2 translation or whatever to map it to somewhere that makes sense, so that you could indeed do that precise application. So yeah. Games.
One question. The DCD also involve the Gen Z memory. I mean, you mentioned here the DCD is just for the 6L Type 3, or it could also serve for the other memory pool technology, such as the Gen Z memory module.
The software solutions being developed could apply to any other hardware solution or any of this stuff. Absolutely. If you've got something that looks a bit like this, that's not this, then we need to have that conversation as soon as possible so that we can try and share some resources and work, and hopefully, yeah, get a common solution that works for any system where you've got the same properties. There are some extra challenges. Sorry, I'm just going to move on because we won't get to the end otherwise. There are some extra challenges around orchestration of this. We have interleave going on. So although you've got dynamic capacity, it might be coming from, well, up to 16 separate devices, all of which are presenting an individual event saying this new bit's available. Obviously, there's a bit of orchestration there to say, well, we can't plug it in yet because we're missing some of the interleave set. So once it all turns up, you can then instantiate that. There's a bunch of policy around this to be developed. Like if you get a new chunk of dynamic capacity, do you try and stitch it into an existing DAX region and say, well, your region got bigger, or just create a new one? There is a bunch of infrastructure built into this as well, which is intended for tagging memory such that the idea is the orchestrator says, I'm launching this application on these servers, they need some more memory, and you can pass this memory with a tag that says it was for this purpose. It's completely opaque. It's just a magic, is it UUID, or it's a big number. And that allows you to have applications then come down and map the memory that was intended for them. And so there's a bunch of stuff to be done to get that information to the right places. Yeah, and the last note here is the one that already exists for 6L Type 3 devices if they are memory that is suitable for normal use. You have a question of whether it makes any sense to map this stuff through as normal memory. In this particular case, because of the sparsity side of things, I think this is, if you did it, you would need something that looks a bit like is already done for VirtIO mem. where you have this option to have a sparse physical address range, but still map it as normal memory. So I already did tags, so we can skip that one. Interleaving we kind of touched on with the many events there. The last one is the one that makes us all a bit exciting for how we go about doing it. So how long have I got? So I'll give a very quick introduction to this. So this is sharing. So in sharing, we are presenting the memory to multiple hosts. Same underlying memory. It can be hardware coherent. So you can have no need to do any special maintenance, any flushing, any of that stuff. Because CXL3 introduced back invalidate and all of the usual stuff to enable a coherent protocol. Now, there are some quirks, one of which is because you have, we say, a problem with fragmentation after you've been running one of these devices for a while, you may well have a situation where you want to share some memory to two different hosts. Both of them are using host physical address space windows to access the thing, and you don't actually have a common physical address space that you can use. There's nothing in both hosts that is available on both of them. So this means that you end up in a situation where you have to map them to different addresses. So the view seen from each host is different. And then just for extra comedy, there's no particular reason they have to either be the same size chunks or in the same order, which means that you get this situation where your host is getting presented with stuff that you're sharing across multiple hosts. The physical address ranges that they're seeing on each host are effectively scrambled, but you do have the information to rebuild that. So when this was getting defined, one of the requirements was that it would be possible on each host to build a contiguous mapping. So you can map it up into virtual address space and have a contiguous region. Whether that makes sense is an implementation choice, but you can at least ensure it looks the same on each host to some extent. So the issue and the reason I raise this is the complex case. And there is a question for, if we're getting into questions like the sparse case for KMEM, and whether we're trying to handle that, how we handle things in DAX when we can have holes punched in the middle of the memory range, all of that side of things. And now we have a question where we actually have a use case where we need to be able to reconstruct the order of the things. The order matters. We do at least have the advantage that, as far as I'm aware, for sharing, you're not allowed to free random chunks of it. It's freed on a tag basis. So you can take out the whole thing or none of it. Or if you want to create some more, you create a new region that's tagged separately. So we don't have the complete insanity of ending up with shuffling what's in the share. This is kind of, the question was, do people think that our best approach to this is basically to ignore sharing for now? It brings a lot of extra complexity with the possible disadvantage that we end up with an entirely different solution for the shared case. Or is it worth trying to architect the whole thing from the start and possibly getting nowhere for quite some time? So we have one final slide, which is very loosely termed the plan. The very first thing we need, and I'd certainly be interested to hear if that FEP model we had in the previous talk is going to support any of this stuff, is we need a platform. Yeah, it's been in the spec for a month. It's going to be a little while before there's any hardware. And more to the point, it's going to be even longer before there's any sort of hardware generally available to anyone who's developing for these platforms. I'm sure there'll be a number of prototypes in different places. They're useful for testing, but we can't really develop against them. So we need some emulation. So step one, in my view at least, is emulate it. FEP is great from ARM, but we'll also do something in QEMU. And then the question becomes, my proposal is to do the simple case first. Let's get something working. We might not actually merge it, but let's at least check that we have an RFC that works, that allows people to look at how this is going to be used, start developing applications against it. And then later, move on through extra complexity, make it dynamic, have the ability to punch holes in the middle of an existing region that's been provided to a given host, and then only then hit the complex cases. Shared is one thing. It is possible people are going to do this with non-volatile memory, in which case you get into fun questions of mapping the extents the same as you did last time. So there's extra complexity there, but I'm certainly not hearing anyone caring about that use case just yet. Pools of non-volatile memory don't seem to be high priority. If anyone has a different view, then join in and try and support that use case. So we are running pretty much to the end of time, but we maybe have time for one question or two questions. Anyone online?
A question on the slide 14, yeah, just the last slide, and you separated the DCT region and the 6U Type 3 device. So so in hardware, the Type 3 device is out of the system, and then you still put a DCT device on every server. Is that right? So here the DCT is mentioned a device, and a Linux driver should to enable this device and connect to the 6L Type 3 device.
No. So what we haven't touched on here is what the actual model to providing memory pools for 6L devices is. But the complexity of management of the presentation of the devices is actually handled in the switches in the path between you. Or you can have what's known as a multi-head device, which is, I mean, it's kind of it looks like a PCI device that goes into a slot in two different machines at the same time. So you can do dynamic capacity across those as well. But there is no explicit hardware supporting this on the CXL hosts. So it's in the memory pool in device, wherever that is, or the switch in front of it.
Okay.
That's a whole nother topic, which we haven't got time for.
I have one comment, that maybe it's not question, but comment. I think it means to consider sharing at the first place. It could provide something like more clear abstraction. Because I know many cases when people don't consider something like some idea from the beginning, and that was big trouble. I think maybe it makes sense to think about sharing anyway from the start.
The only thing I would say about that is the software model for anything that's making use of shared memory, it has to be, whatever the actual application is that's on top of it, has to be fully aware that it's shared memory. Because, I mean, much like, you know, a couple of processors sharing some memory, you need to know it's going to change on you, or potentially. Whereas for all of the other use cases, you know, that's not the case. So if we did end up with, I don't know, a different way of mounting it or something to expose it all the way down the stack differently, we'd probably be in a situation where we wouldn't run into the problem of trying to extend the underlying thing. There's no application that you would write to deal with both cases. So maybe we can get away with it, but I take your point that, yeah, don't ignore the complex case, because it might bite you.
If it's simple, start from the simplest one. It's good. Simply go ahead. My point that it makes sense to consider maybe sharing. Keep it in mind with.
Yeah, there isn't a complete separation, because there are things that are more complicated if you aren't sharing, and there are things that are more complicated if you are. But I get your point. Go in for the hard cases at the beginning.
All right. Okay. Let's thank the speakers. Thank you.
Thanks, Abby.
Thank you. Thank you, Jonathan.
Okay, so I'm going to talk about CXL and confidential computing. Same plan as the previous presentation, scare people. And I'm going to go pretty quickly on what confidential computing is, what it means for a device, and then go to finally CXL. So confidential computing, I'm taking the definition from the Confidential Computing Consortium, which I think is part of the Linux Foundation. So, you know, you want a trusted execution environment. It means that your data, you're running inside an isolated environment, and only some, whatever you trust is able to access your data. So usually it means that you can run your workload without the hypervisor or anybody else being able to spy on you or to see whatever you're doing. So it comes with a bunch of requirements, obviously. You need to be able to attest the platform you're running on. You know, if you cannot attest that the CPU you're running on is providing you an enclave, then you don't really exist. You want data integrity, making sure that nobody can modify or alter the data you have inside your environment. You want confidentiality, nobody can spy on what the data is, so encryption, really. But not only encryption, isolation is also very important. And you want code integrity. So that's often seen as an optional thing, but it's also very important if you don't want somebody just to modify the code to extract the data you're running inside your TE. So most of the time, TE is through hardware enclave. So Intel, AMD, and ARM, they all have very different naming for that. Or also have a different naming for that, but everybody has a name for that. But it's just an hardware enclave, really, where your VM, usually trusted VM, can run. The threat really is any other application on the host. The host operating system is also seen as a threat. The system administrator is seen as a threat. The service provider, cloud provider, is seen as a threat. So it means that you're not trusting anybody, basically, in that kind of scheme. You are like a customer, you want to run a VM in the cloud or wherever, but you don't want the cloud provider to be able to access your data or to be able to modify your data or to do anything with your code or application. Bunch of things that are optional, like code confidentiality when you launch your application and so on. So, and also recover things. So, if there is some kind of event that happened, it's not necessarily somebody attacking you, but it might be some our fault happening, some signal integrity and whatnot. So, there's like things if you want to recover from a state of panic, basically. I want to touch on one thing is what I call the pyramid of trust. Is as soon as you have one layer that is compromised by any means, I'm talking generally here, it means that all the layer above it are also compromised. If your hypervisor is compromised, then it means any VM running inside that host is compromised, unless you have secure VM with enclave. So the outcome of that is that if you want to protect and create enclave, the only way to be able to achieve that is by having the hardware as the lowest layer, is by protecting making the trusted execution environment inside the lowest layer. And so like the security is as strong only as the lowest layer. So one of the bonuses of making the enclave inside the hardware is that you can remove the operating system and the cloud provider from the trust base. So it means, if the enclave is provided by the hardware, you don't have to trust the operating system, the BIOS and whatnot that is running on your computer. So roughly the architecture, how it looks when we're looking at VM, you have the CPU with a security module, you have your hypervisor, which is like most likely Linux. With this Linux Plumbers after all. And you have the trusted VM. And basically what happens is that whenever you have memory that is assigned to the VM can first authenticate the memory and say, okay, I'm accessing that memories, and talk to the CPU security module, and the CPU security module gonna program a bunch of table and isolate the memory from the hypervisor. And at that point, the trusted VM can start using that memory. And so that you have like the security module that's enforcing isolation from everything else in the system. So what it means for device is that if you want a trusted execution environment in the device, you want the same kind of thing, really. You want to be able to attest the device. You want that the device protect the integrity of the data. You want the device to have confidentiality for your data. You want the device also to have code integrity for the code running on the device. And again, you want that to be in hardware. Same as for the CPU, really. But again, same as for CPU, you cannot trust all the block inside your device. Your device, like I'm presenting here a very basic abstract device, and your device doesn't can have so many blocks that you cannot really trust every other blocks. So usually you have the idea is that you have this kind of root of trust, and then everything else falls from that block. Another issue with device is that you also have to think about one hardware block can be used to attack another hardware block. And so you have to think about boundaries and what you can do also for debugging and so on, because often devices, unlike CPU, have not been isolated as much as a CPU really. So it means that when you look at debugging feature on I don't know, a GPU, for instance, or some kind of accelerators, really. Often, if you use JTAG or whatnot, you can access the full states of a block, which means you can also access the data as an inside an hardware block. So, which means it gives you a window into the whatever application is running. So, if you want isolation, you want device enclave. So, the way we're doing today with PCI Express is things like SRIOV and so on. So you can have a virtual function that is assigned to a specific TVM, and only application inside a TVM run inside an enclave on the device, and the device can isolate every virtual machine workload. So yeah, the check-click really is trusted execution environment, root of trust that gives you attestability, the way to measure device, device isolation for integrity, confidentiality. And obviously, you also need to protect the traffic between the CPU and the device, and that's going to be really the chunk of the talk here, because CXL is in a fabric. So the issue is you want to protect the communication between the CPU and the device. There's many ways that somebody can attack that traffic. You can have a PCI Express switch or a CXL switch between you and the device, and somebody might have taking control of the firmware of that switch, or you can have a cable and somebody just puts some kind of interposer between you and the device. And what the attacker can do is like modify traffic, inject traffic, delete traffic, replay traffic, spy on the traffic, look what is the data, and also do side channel. So it's like, this same memory has been written again and again with the same pattern, same memory. That might be a way to guess something. So the integrity is going to protect the first four actually, and yeah, well, the encryption is going to protect the last two. So integrity, the idea is that for every message you have on your fabric on PCI Express, CXL, you want a message authentication code. So it's basically a hash of your messages, a cryptographic hash of your messages that say, okay, you need to know the key to be able to compute the cryptographic hash of the messages, and it will protect you against all the first four, like modifying traffic, being able to replay traffic, because you also use a counter usually. So it means that both sides look at every messages and they have a counter, they keep incrementing and they keep in sync. So it means that they expect to have a certain number of messages. So that's for integrity. For encryption, the idea is that you only protect the data. You're not protecting the address, OP code, or whatever of the traffic. You only protect the payload of a PCI Express. So it can be a memory read, so you're going to protect the memory, not the address or things like that. Usually, you also want to use some kind of salt or counter again, because if you use the same encryption, depending on the encryption algorithm again, if you use an encryption algorithm that for the same data give you the same output result, then somebody can use that as side channel attack because he's seeing the same pattern being written again and again. And so that's also a way you want to protect yourself against. Another thing you want to do, because you have context on both sides, you have context on the CPU side, your trusted VM, and your trusted VM going to have a context on the device side too. And so you would like to be able to assign traffic, so you know that one traffic message is assigned to a specific context on the device. Otherwise, a context on the device might pretend to be attached to a different context on the CPU and be able to spy on that other CPU context. So that's one thing you also would like to have. A touch on topology. So, you can have very complex topology, especially with CXL. So you can have like a CPU connected to a switch, and the switch can be connected to a fabric, and the fabric is multiple switches, basically. Any number. There is no limit, I think, on CXL, like 4,000 maybe, but can be a big number. And so you can have like, many devices between the CPU and the end device. You can have many switches. So that can be an issue. So you have two kind of encryption and protection. You can do point-to-point. That means that you go from CPU to first switch, encryption and integrity between the two. And then the first switch is decrypting the traffic and re-encrypting again for the next destination. And so it's up to a point-to-point. So, from one point to the next, which means you have to trust every single point in the path. Otherwise, if any point in the path is compromised, then that point in the path can escape the traffic, can access the traffic in plain text. So you completely lose your protection if you do a point-to-point and one of the points is a weak point. And if you do end-to-end, the idea is that only the two endpoints need to know about the encryption keys and the integrity keys, and only the two endpoints can understand each other. It means that any point in the fabrics, it's just passing along messages. So if you think of it as like TCP and SSL, really, like, you have a packet that is protected by SSL, and all the switch on the internet, they're just passing along packets. They don't care about what it is, or should not care about what it is. So that's the big thing about computational computing and what it means for CXL. So maybe a quick overview of CXL. It's really a new protocol that is geared toward cache, kernel, load, and store. It allowed to add memory to CXL that behave like the main memory you have. You can also have accelerators and so on. And one of the things you have to understand from that is that it's dealing with cache line, 64 bytes. So it means that every message on CXL cannot have a header, or the metadata for the message cannot be too big. Otherwise, your bandwidth efficiency is going to be really bad. If you have more than 64 bytes to describe the 64 byte of data, then what's the point of your interconnect really at that point? So you want to have very few fields, and that's what CXL has, very few fields. Just opcode, the physical address, and few ancillary bits. So there isn't much for the header, basically, which is an issue for security. One of the issues with CXL, it's all about physical addresses. So it's HPA host physical addresses. So there is no IOMMU, there is no filtering of anything. If you are CXL devices, type 2 or type 1 devices, you can access any memory on the system. And you have full access. That's what the specification says, really. So there is no IOMMU, nothing that can block you. So it means you must trust the device, that the device will not try to read or write or snoop to things that it should not. And there is no more central access control. You don't have a IOMMU or some central point where you can program the access control. It means that you have to program access control everywhere in the device and every device you might have. So that's one of the issues with CXL when it comes to security and computational computing. You have to keep in mind. Another issue is traffic identification. So I talked about it. When you have multiple contexts on the CPU and on the device, how do you identify the traffic? Well, you can't. There is no way to assign an ID inside the header, so there is no way to identify traffic on CXL. So when you have a device asking the CPU for a specific cache line, the CPU has to trust that the device is authorized to access that cache line. There is no way for it to know if the context on the device is actually authorized to access that. Another one is CXL IDE. So CXL IDE is like PCI Express IDE for those who know it's integrity and data encryption. On CXL, it's only point-to-point, which means you have to trust every point in the path. Kind of bad for a TCP. So TCP is a trusted computing base. So it means everything you want to trust. And if you want confidential computing, you want to limit the trust to TCP. You want to limit the number of devices you trust. The more people you have to put inside your circle of trust, the less, the more scary you should be. And the last one really is ROC devices. So CXL memory device, all the ones that are going to hit the market have an ARM CPU really, or a CPU. It doesn't have to be ARM, but so far I'm only seeing ARM. And it's pretty powerful. So, it's not a simple microcontroller. We're talking about like powerful CPU core actually. And, how do you feel about that? How do you feel about having a CPU in your memory, really? Because that CPU can access all the memory, that is CXL memory. So yeah, maybe you should be scared about that. So what happens if the attacker takes control of the firmware? Anyway, because they manage to break the device, or they supply chain attack or whatnot, or they find a bug in the firmware and they are able to live attack the firmware. And they can also use that to escape memory. So you have 2 TVM on one CXL device. You have like the device sniffing out one TVM context and escaping it to another TVM context. So we talk about multi-host. That's even more scary if you think about it, because you can have multiple hosts and one host can be attacking another host. So, like the host thing is like you have multi-fabric, server A, server B, and they're all using device A and device B, and they can use, server B can try to use device A or device B to attack server A. That's also scary. And finally, the multi-head thing, we also touch about it. It's kind of same model. Instead of having a switch, you just have a device that has multiple connection. So it's like a switch and a device integrated together. But you can have multiple different hosts connected to the same devices. And again, that device will have a firmware, will have CPU and so on. So you can also attack the device. Anything else that scares people with CXL? Like that's all the thing that scares me, but there is probably much more that you should be scared about.
Hey, Jerome. Working? Okay.
David, can you draw your?
Test.
Yeah. So you mentioned about the issue with no IMMU in the path. That's not technically true, although it's certainly possible to not implement one. So CXL devices are obliged to use ATS if they're accessing host memory anyway, which is fine. And the problem with ATS is always you're saying, I've translated it, and nothing believes you. Now, the specs were always written with the intent that it was perfectly permissible to put a checker on the path, and that's definitely an option. Whether anyone's done it in their host, I have absolutely no idea. But
yeah, so technically it's true. Like a CPU can add some kind of IO menu to block CXL traffic and only allow some addresses to be accessed by specific devices. So technically it's doable. But I don't think any of the CPU makers is actually looking into doing that, as far as I know. But and as far as we can say here, also, yeah.
But I mean, if it is a security concern, it's one of those things that I know has been discussed in the past as perfectly doable. It requires some slightly exciting caching.
Yeah, it's not so much of a security concern as it is like something we want to keep in mind. So it means that if we want to have access control, then it means we need to have access control in the device, and we need to be able to trust the device to enforce the access control. And that goes back to all the complexity, like, making a device secure is not that easy. It's not, hey, I just have like some controllers that run something. No, one hardware block inside your device can be attacking another hardware block, and like you have debugging port, a JTAG port, and whatever. And so like it's holistic, really.
Yeah, no, absolutely agreed. It's in the same category as anything inside the actual host.
Yes.
Looks like it is.
So to add to what Jonathan just said, I can say for a fact that at least Intel CPUs do perform ACS upstream forwarding filtering. So unless you've enabled ACS upstream forwarding, all the traffic will be filtered. So that works at least on Intel CPUs.
I was just gonna ask, on the slide we had all the integrity and confidentiality attacks. You had like 6 or 7 of them. obviously we want to protect from everything, but it can be useful to distinguish between physical access attacks versus software available. And I feel like you actually sort of touched on it later on when you said if someone figures out how to hack, say, the firmware on the device, which and then the device has these, especially without the IOMMU. But I'm just curious, how many does distinguishing between a threat model where you're actually worried about someone getting physical access and like putting a probe on the cable make this a little bit easier, or is this in your view all in play even for somebody who only has a remote connection?
Yeah, for me, I just like see it's all in play because right now the switches have a very complex firmware. So the attack surface of the firmware is so big that I assume it's very easy to attack a switch. And also I assume that technically a switch is like a physical interposer, really. So yeah, I don't see the physical aspect as a problem here.
Makes sense. Thanks.
Do you get device to device? So I mean that one there shows CPU to device, and most of the other things show boxes of RAM. Do you get GPUs talking to GPUs or things like that?
Yes, you can. So it's something we'll look into peer-to-peer, really. The able like device A talking to device B, and then again, you want to be able to trust both devices, or at least trust the context in each of the devices. I thought I had a slide about that, but yeah, okay.
And also, do you get multiple paths? So do you get redundant paths through the fabric with different encryption potentially?
Yeah. So so let's not talk about multipass. It does not exist today in CXL. Might exist sometime in the future. Nothing.
I was wondering what the plan is for auditing all the firmware in an open source form that runs on all these devices.
I wish. so I wish like all the firmware on these devices are open source, and that they can be audited by everybody, and that you can also sign them and have a properly solvable bill and so on. But I think it's not going to happen quickly. It's something we're working on, I think, with many of the CXL SoC provider. But yeah, I don't think it's going to happen. And also the biggest issue I think we have at this point is that the hardware itself is not secure. So even if we secure the firmware, there is a way to attack the hardware easily. So first secure the hardware, making sure that your hardware is secure, and then the firmware become like the next big thing we need to tackle. But doesn't mean we have to do one after the other. But yeah.
Is there a blueprint from like enterprise SSDs right now? Like they have powerful cores right inside of them. So like a lot of the concerns I think that you have already exist in
NVMe.
Yeah, in NVMe, right? And I guess like that isn't that the blueprint for doing this? And if you can fix it there, like CXL, I guess the big difference I see with CXL is that it becomes host memory, right? Which is that's the big difference, right? And maybe, but all the other concerns already exist with NVMe.
Yeah. So with NVMe, the thing is like you have encryption often happening before you eat. So either before you eat this core, the data they get is encrypted already, so they don't have access to the plain text. Or when they do have access to the plain text, it's only a small chunk inside that complex thing that has access to the plain text, and then it's all encrypted.
Hey, Jerome. So a couple of questions. So one is, can you comment on the CXL types that really apply here in terms of scope? Because I was just thinking of if you think of a type 3 device, like a memory buffer device, you might have an approach where the CPU SoC encrypts data before going out to those dumb device. Let's call it a dumb device, just storing, not doing any other additional things that needs clear text access.
Yeah, so for type 3 devices, that's the easiest solution, because then it means that whatever is leaving the CPU is encrypted, and nobody else outside the CPU knows about anything and doesn't need to know about anything. And so that's the easiest and the more secure solution that you could do. Sadly, not every CPU necessarily support that.
That's true. So the type 1 and type 2 it sort of seems like the more
Yeah, type 1 and type 2 are going to be more complex because, so far a GPU that will need to do some real work will need to have access to plain text. We don't have.
Right. And then the other related question I had in the PCI SIG, where we have IDE, we also have selector stream, right, which does end-to-end, as you're suggesting. Can you comment on what are the issues here with CXL that don't allow us to do end-to-end?
I mean, I could comment, but it will take hours. So basically, like the complexity is too big. So like the reason why you can do on PCI Express basically is because you have only 3 channel on PCI Express. With CXL, you have 12. So you have a state explosion. So you have to multiply 12 by 4,000, and then you have to look at the number of bytes, and then you look at it, give you the number of SRAM you have, which is multiple megabyte of SRAM you will need if you want to keep performance good, which means the cost is crazy. And if you, so it's like just like when you add up the number, it doesn't scale.
There are some other bits around what you would have to expose because the addressing is part of the routing on CXL, and often the one thing you want to protect is what addresses you're actually accessing.
Right. So I can see the key state explosion thing Jerome is describing.
Yeah.
But yeah, I think we should talk more about this.
It's tricky, but talk to your favorite CXL consortium rep about it.
I assume many people here in the room are actually working for companies that is part of CXL. And so you should really go talk to the people working on CXL in your company and tell them, oh, I actually see something scary because it's really scary. And, we talk about all the nice things we can do with memory pooling and memory sharing and so on. But, if we don't have security in the end, that's going to be even more scary. So.
Yeah, I mean, memory sharing with confidential computing doesn't really work anyway. So.
Very use case actually for that, but yeah, it's like.
All right, let's thank the speaker, and then we'll come back on time, start on time. Thanks a lot.
Thank you.
I love the cloud.
why weren't they working? Well, who knows?
There.
Start. Okay. Let me start. Okay. Okay, hello everyone. I'm Higon Prab from Samsung Electronics. I'm going to talk about the auto caching for byte addressable CXS storage devices. The auto caching can support the DEX and the page cache at the same time for different blocks on the VFS layer, so that the application can use the page cache for the hot data and the cold data, the DEX for the cold data. Okay, this is the agenda today. I'm going to talk about the motivation first, and then discuss the design and implementation of auto caching, and then challenges. After that, I will show the preliminary result and our next plan. Okay, let me start with the motivation. So with the CXL, we're gonna have many new types of storage devices, like dual interface CXL SSD, byte addressable storage devices, or many different kinds of the, computational devices. This slide shows the dual interface CXL SSD and the byte addressable storage devices. Left hand shows the dual interface CXL SSD. As you can see, it can support the .io and .mem at the same time. So application can use the .io for throughput-oriented the workload, while it can use the .mem for the latency-sensitive data. For worst case, auto caching can handle I/O efficiently because it can leverage the DRAM and the device memory at the same time. So we conducted some performance measurement with using the Optane. Actually, unfortunately, the CXL SSD cannot support the .mem write yet. So we're gonna have a plan to implement the .mem write next quarter. So next year will be available to test. So that I use the Optane for the test because the Optane can support the byte. Optane is a byte addressable, and it is pretty much the same to the functionality. So as you can see, the left side, the page cache can show the better performance than the DEX, regardless of the number of threads. The right-hand side shows the performance number with a different working set size. As you can see, the DEX shows the almost the same performance regardless of working set size. However, the page cache case, the performance is dropped down dramatically more than 90% when the system is under memory pressure. So from the experiment, we learned that the page cache may be a better option if the system has enough memory. But if the system is under memory pressure, then it's better to use a DEX. So the next test is a write test. So unlike the read test, DEX can show the better performance than page cache, even the system have enough memory. This is because the flash daemon continues to write back the dirty pages to the device and interferes the applications because it can hold the pages to write the data to the obtain, and the obtain case it also pollutes the CPU cache. However, we increase the number of threads, then DEX shows the poor performance than the page cache. This is because Obtain could not support concurrent write efficiently. This is very well known in the community. And the right-hand side shows the performance number with a different working set size. The trend is exactly the same to the read performance. However, the page cache still shows a better performance than the DEX because the DEX should have DEX cannot support the concurrent write efficiently. So from this lesson, from this the experiment, we learned that even if the system is under memory pressure, if the concurrent write happen, then the page cache may be better option than the DEX. This slide shows the simplified block diagram of page cache and DEX. I think I don't need to explain all details, but what we want to is that we want to merge them into single layer and support the DEX and the page cache at the same time. So hot data can be placed in the DRAM and accessed through the page cache, and the cold data can be placed in the PRAM and accessed through the DEX. Fortunately, it is very simple to implement because the Linux kernel already have most of the data structure, and we just use the existing data structure to implement the auto caching. For example, the Linux kernel already create the device page structure and also create the direct mapping area in the kernel virtual memory. So that what we need to do is that we simply insert the device polio into the file map instead of page cache to use the DEX. This is a little bit detailed architecture of the auto caching. So we mainly focused on the auto caching layer and the cache transition. And the auto caching layer manages the device pages. And in order to manage the device pages, you need to know the device memory physical address, right? So that the PRAM driver can provide that the range when it is initialized. After that, the auto caching knows the device memory range and manage it internally. Once after that, whenever file system is mounted on the system with the auto caching option, then the file system try to figure out the file system can use the auto caching or not. So if the file system is built on the PRAM, then it can use the auto caching. So auto caching layer returns the auto caching range to the file system, and the file system keeps that range in the superblock memory object. That means we don't need to add the auto caching range into the superblock device format. That means we don't need to change the superblock device format. We only keep the auto caching range in the superblock memory object. After that, the file system knows whether it can use the auto caching or not. If so, and then whenever the user send the read-write system, call the read-write system call or page port handler request the page, then VFS try to find the page in the file map. If file map node is empty, then the VFS try to allocate the page or folio. But if file system has the auto caching feature, then it try to get the device folio first. But the auto caching layer have a responsibility to determine whether the page cache is better or the device page is better. If auto caching layer decide that the page cache is better, then it just simply returns null. Then VFS will allocate the page cache and insert the page cache into the file map. Otherwise, if auto caching decide that the device is better option for current situation, then it takes the block number from the file system and converts the block number to the physical address and the device page and return the device page to the VFS. And then VFS can simply insert that the device page into the file map. After that, everything is the same. Just like the page cache, because the page cache can be converted to the physical memory of the DRAM memory, and the device page also can be converted to physical address of the device memory. So I explained about the framework so far, and the framework itself is very simple to implement. So the total number of the lines to be changed is less than 200 lines, and the VFS layer and the file layer modification is less than the 40 lines. And we also need to implement the caching transition layer, but I'm gonna explain about that later. But we have 3 challenges. The first one is the space overhead of device page structure. And the second one is a cache transition. And the last one is an allocation policy. Okay, space overhead of device page structure. First of all, the page structure, the size of struct page is 64 bytes per the 4K bytes the page. So that if we add 4 terabyte storage devices, then we have to reserve the 64 gigabyte DRAM, because the page structure is metadata and kind of hot data. So we need to keep the page struct page. We want to keep the struct page in the DRAM. But the most of device page structure is not actively used. Only opened page can use the device struct page. Otherwise, if the file is not opened or block is not mapped to the file, then the page is never used by the system. So our solution is that we want to allocate the page structure dynamically. So in order to do that, but before that, if we allocate the page structure dynamically without any information, then it is very hard to convert the physical memory to page structure or page structure to physical memory. It's gonna be very challenging. We may need to use the hash table or something like that. In order to avoid that, the complication, we use the thumbnail paging. For that, we create the page structure per 2 megabytes. So that means the single page structure can cover the 2 megabytes, which is equals to the huge page size. So if the file system uses huge paging, then the device system can directly use that 2 megabyte structure page. But so if we use a 2 megabyte page, then we only need 128 megabytes for the 4 terabyte storage devices. And if the file system wants to use a 4K byte page structure, then we need to extend the 2 megabyte structure to the 512 structure pages, so that we dynamically allocate the structure page, the 512 structure pages, and convert the 2 megabyte 2 MB structure to the thumbnail page. So the thumbnail page can point to the base address of the 512 structure pages. In order to access the 4K byte strategy, 4K byte structure page, we need to divide the PFN into 2 parts. The first part can be used as the index for the thumbnail page, and the other part, the 9 bits, can be used for the 4K byte page index. And we also changed the information in the file map node. Actually, for file map node, keep the struct page address, but we store the page frame number instead of the address of struct page. Because we want to use a sum of bit for the one page detection. I'm going to talk about that part later. This is the address conversion macro. So originally it's very simple. There's just the page minus the mmap or mmap plus PFN. We can convert the PFN to page or page to PFN. So we changed the structure of a page, the page structure. So we need to change this conversion macro. So the PFN to page is pretty much simple, but page to PFN little challenge. So in order to convert the page to PFN, the first simple solution is that the page, we can simply add the PFN into the page structure. That is the simplest way, but it can increase the size of a page structure. In order to avoid the increase the size, change the size, increase the size, we can use a reverse mapping. So the page structure have an address mapping and offset. So it can find the file map node, and the file map node have the PFN, but it is a little bit complicated. So instead of that, we can reserve the virtual memory area in the VMLOC, but we don't need to allocate the physical memory immediately. We just allocate the 64 GB virtual memory only. And then after that, if the application or kernel need to the physical memory, then we allocate the 32 KB physical memory for 512 the page structure and the create mapping. After that, if it doesn't need to used by the system anymore, then we can free the physical memory only while keep the virtual memory. So the virtual memory can, if we made that kinds of virtual memory, then we don't need to, we can use the macro as of now. Next one is cache transition. It's a little difficult and little challenging for us. Yep.
Can you hear me in the room?
Yep.
I was going to ask, back a couple of slides, you said you're talking about the classic 4 terabytes takes up 64 gigabytes of RAM problem. Another and dynamic page allocation is one way to solve it. The other way that PMEM solved it is to allocate the struct page data from the device that's adding that much capacity. So if you're, yes, 64 gigs of RAM is a lot, but if you allocate that page structures from the NVMe device, since that's the one that's bringing on the 4 terabytes or multiple terabytes, then the relative overhead is less because it's coming from a cheap device. Did you explore that?
Yeah. So yes, well, we get that, but the CXL SSD is extra challenging from a media perspective, right? Right. So like rough implementation, there's DRAM behind the NAND, right? Like NAND is slower media than DRAM, right? And you present that memory interface, and writes are even more challenging for NAND, right? So I get it, but putting them on the device is probably not going to be the solution for this, right? Yeah. Does that make sense? Based on the device properties.
The device is too slow for struct page. Got it.
Something like this.
Let me continue. Basically, we want to use the mechanism that used in the tiered memory. So for the demotion, it's very reasonable and very effective, and the tiered memory also use the sub out mechanism. So we simply select the victim page from the inactive list when system is under memory pressure. And then we need to get the LBA or block number from the file system, and then convert the block number to the physical address, and after that we update the mapping. This procedure is a little bit different from the tiered memory, because tiered memory have to allocate the slow memory first and copy the data to the slow memory and the change mapping. But this is a file system, and the file already have a block number, and that block already have a contents if the page is not dirty, right? So we simply change the mapping to the device. We don't need to copy the data to the device or allocation page. But the most important thing in the auto caching, that we want to keep the one page inside the device, but the autonomous mechanism may not good solution for our purpose. So we devised a new solution. That name is is a FlexZone. So FlexZone try to keep the one page inside the device. So a promotion daemon virtually promote the access the page to the FlexZone, but not physically move the data to the host memory, and keep watching whether the page is really hot or warm or cold. In order to implement realize this one, the FlexZone has a limited number of pages. For example, the FlexZone have threshold 10, but if the number of pages increased over the 10, then the differences will be promoted to the host memory. But the page can ping-pong, right? So it can be demoted again. So if it demoted again, then we detect the ping-pong happens, right? In that case, we increase the FlexZone and keep the more page inside the FlexZone to keep the more one pages. But if the FlexZone is very stable, there is no movement anymore. That means if so, then we increase we decrease the FlexZone size and promote the sum of the page. So we want to keep the one page as much as possible inside the device. But another thing is we need to detect which page is warm, right? So in order to detect which page is warm, we use a 4 metrics. So first one is the IO type, second one is the access cycle, and the third one is the access frequency, and the last one is a recently accessed page. In order to get this information, we use some bits in the file mem node. So file mem node have contains the write ID and the access count. Write ID can be used for the identify the concurrent write. So different ID can be written to the device at the same time, right? And we use the access count for 12-bit for access count, but it divided into 4, divided by the 4, and each reason used for indicate the specific period. So we pretty much keep the history, right? So if the current period to third period have some valid value, that means the application periodically access the page. If so, then we give a highest priority to promote for the page. And we also consider the access frequency. So each period have 3 bits. So maximum it can count to the 8 access. But if the application access the more than 8 times, then the page can be promoted immediately, because the page is heavily used by the application. And we also consider the recently accessed page.
Does that solution need to be separate? Like we have everybody working on memory tiering. Like, does this engine need to be separate from the memory tiering engine that other people are building? Like, shouldn't it be integrated? Or it needs to be separate?
So this is a good question that yeah. Why would this be any different than any other memory tiering, but just with different properties, right? Is kind of this asking the same thing, right? Why would this be separate than any tiering out there? What would be the difference, right?
I actually thought here the memory mechanism is working for the system memory, right? It doesn't have any persistency or something like that. It doesn't relate to the file system. So auto caching is similar to the tiered memory, but the target is different. Our target is a file, not the memory.
So maybe does there need to be a separation for page cache specific tiering in any way? I think that's more the general question.
Yeah, is all the tiering now based on anonymous memory? Like, do we need file back tiering?
I would look for you, Dan, on that. I'm not as sure, right?
Oh no, yeah, no, I was. It was for the room. It was for the plumbers conference. Like, maybe this is a concept we need to think about as a community.
Yeah.
Time for questions.
Okay.
So first of all, I believe that this technique cannot be extensible for another file system. And mostly it's dedicated to ext4. And if you're talking about SSD, a lot of file system, it's using copy and write policy. And it means that this technique cannot be used at all. How do you see that? Because on slide 10, it mentioned file system without any particular file system type. Or it can be, maybe it can work for ext4, but it cannot work for other file system. How it can be extended?
So actually, you're right. We implemented on the ext4 file system, but I think it can extend it to any other file systems.
No, it cannot.
Why?
I file system developer, you cannot, for example, extend it for copy and write policy that file system use copy and write policy. F2FS, it cannot be extended for F2FS. It cannot be extended for NILFS2.
So actually, the auto caching layer pretty much isolated in the separate layer, and we don't need to file system change it so much.
Again, every file system very specific. And for example, if file system using copy and write policy, it means that application don't know where real data is located. Only file system know. And it's not so easy simply take something from SSD. It will be some garbage. You don't know what is it.
I think the point is not for this to generically work for everything, right? Yeah. Right. So the model where this makes sense is where you allocate ahead of time, right? And you carved out the space that you're using, and then use it afterwards. In other words, more like a DAX-based approach too, right? Where you map to the physical address ranges, and you generally know that more ahead of time, right? Like that it's like it's used to carve out address ranges that is not as dynamic, right? So I think that kind of model should work for this.
Yeah, you need to specify that it's DAX-based.
It's DAX-based. Yeah, that's definitely shown here.
One of the observations about so like ButterFS and things that have not been DAX enabled, but people are working on it. But one of the observations is that for reads this should be okay. Like a DAX access for reads is, but yeah, certainly on the right side, DAX is not there yet for copy and write file systems.
I think we should probably move on a little bit and try to wrap up. So yeah,
Oh,
a little bit over time.
So okay, and actually this the over there we need to consider the device characteristic because each device have a different features or characteristic. So I think it is better to provide the policy control parameter to user space. Okay. And I just want to skip the allocation policy is because it is very intuitive and there's no arguing, I think. And this is a performance results, and actually it's a very not interesting. The auto caching just show the same performance to the one that shows the better performance between the DEX and the page cache because the auto caching can use the both of them in it depends on the situation. So for example, if the system has enough memory, then the auto caching can allocate the page cache for the read intensive data. And this is the right results. And there's a little different performance differences between the DEX and the auto caching. And actually I wrote the reason behind below the table, so you can read it. Okay, so we implemented the framework so far, and we need to implement a dynamic structure page allocation or cache transition or something like that. And our target LPC date is end of for Q4 this year. Yeah. That's it.
Right. A question? Look at the folio, because like folio is also trying to like
Folio?
long term.
Yeah.
To,
so actually, we use the 5.18. It already have a folio feature, and we allocate the folio. Yeah, for folio device page.
Yeah, for dynamic strict page allocation also, like for dynamic folio allocation, I guess, because they also it's on the roadmap too, like kind of.
Yeah. So yeah, we have to consider that, and we that changes.
And I can like one of the thing when you said page to PFN, one easy way to solve it, page to PFN, is like because you always have this 2 megabyte strict page, it means when you allocate 512, you have the first one that is free for you. So you have the strict page for the 0 page that you can use to store the PFN. Just again, we can do that offline. Okay. It's like on the graph, it's very easy to show. Sure.
Let's thank the speaker.
Okay, thank you.
To switch.
All right. Great, thanks. All right, well, thank you. You're in luck. This isn't a terribly long presentation, so we'll probably be able to make up some time. Okay. All right. So this is going to be a little bit different than some of the talks. It's not going to be as deep in the guts. It's much more about talking about implementation that we have in the kernel, what's actually happening in CPU host roadmaps, enablement, and how does that align with the spec, and how do we manage this giant mess when people actually want to build actual CXL devices. So it's really more of a, where are we seeing it from our use cases, how is it affecting us, and trying to spawn some collective groupthink to think about how do we actually address this if we think we can. So my name is PJ Waskevich. It's been a number of years since I've actually gotten up to speak at one of these. So this is kind of exciting to be back in person and seeing half of people's faces. And yeah, so I also work for Jump Trading. So brief overview. I won't bore everyone with the obligatory what is CXL slide. I have one, we'll look at it, but I'll focus specifically on certain things because hopefully everyone in this room knows what CXL is at this point. But more importantly, I'd like to look more at the roadmaps versus spec roadmaps, kind of where we are, for those of you who aren't in the consortium and don't really track that very closely, kind of cover where those are, and then cover where do we think some of these features are actually going to intercept on host CPUs, because that's really the important thing. We can talk about all these great features all the way through CXL 3.0 and beyond, but if we're not going to see them in 6 years, then it's just exciting slideware at that point. Then to kind of bring that together, I'd like to talk about our use cases that we're currently looking at with the use of FPGAs and testing CXL and playing with it. And suspect that other people would be in the exact same use case issues. So we thought it would be pretty important to bring up. And then go to some proposals, specifically around hot plug. And that's really what this is about, is supporting CXL hot plug. And I'll get to it there. Okay. So everyone probably has seen this slide multiple times throughout this entire week. Jonathan had a wonderful presentation yesterday on CXL and Meta's use of that. And slides are over here. And so why I'm actually here is I think the majority of the world has been focusing a lot on type 3 devices. So building memory expanders, the whole tiered memory push, ways to build DDR4 shelves over CXL because DDR5 is very expensive and we can get it very dense and very cheap. These are all things that have been getting demoed over the past year, right? Supercomputing had a bunch of demos last year on this. So that's really been where a lot of the focus is. If we look more at this first one in type 1, there hasn't been a lot of focus there. It's been a lot, if there has been, it's been a lot quieter. And this would be like network cards, right? NICs, that I can actually have a CXL.io, potentially have a cache accelerator, do some various exotic things with that. But we do have an issue if we want to look at that and then merge that with today's use cases. And one big issue is this table right here. So take a lot of these with like hand wavy grains of salt. I didn't even attempt to put dates down because they seem to change constantly. But today we have 3 versions of the spec that are ratified and released, right? We have CXL 1.1, 2.0, and 3.0. 3.0 was a few months ago, and we're actively working on next generation stuff, pulling Gen Z IP in there. So it's really cool stuff, right? But we're like light years beyond what the reality is, and the reality hasn't even happened yet, right? So CXL 1.1 is supposed to be showing up on the x86 side in Sapphire Rapids, which has not shipped yet. AMD's Genoa has also not shipped yet. And oddly enough, NVIDIA, with their Grace CPU, has announced that they will support CXL, but they'll support CXL 2.0, and they have not shipped yet. Then when things actually get interesting, right? CXL 2 has a lot of, I would call more core features that are making it much more useful. That's not until Granite Rapids, that's not until Turin. The Ampere, next generation Ampere might have it. And then CXL 3.0, which is where a lot of the work has been going on, we have no clue where that shows up, right? That requires PCI Express 6. So roadmap-wise, we're looking at least 6 years for that. So, anyone want to dispute that at all?
There's some a la carte there, right? Like you could run some CXL 3.0 software features talking to a 1.1 protocol on some of these platforms.
I didn't catch the first part of Dan's comment.
The comment was about software features in CXL 3.0 could be deployed on older protocols.
An awful lot of stuff is back portable So we'll start seeing stuff that's in the CXL3 spec because you can implement it only on the endpoint. You don't need anything on the host. So
Right.
hopefully we won't have to wait that long for some of it.
Yes, yes. We have been finding that things that are officially in CXL 2.0, 3.0 magically sort of work on 1.1. And I'll get to a little bit about that later. So our use case, why am I here? Why is this something that I feel pretty passionate about? So today, in high frequency trading, cloud service providers, telco, anyone who's using FPGAs to do any sort of traffic filtering, network filtering, computational stuff, anything that they have application logic running on an FPGA, typically reprogram those fairly often, right? So I have a new network protocol that I need to look for. I need to have a new field in a header. I have a new, widget that I need to go ahead and implement. I go ahead and create a new bit file, ram it down into the chip, and then we're off and running. Typically, our programming workflow is we have some mechanism to write to the flash down on the board with the FPGA, whether it's memory mapped interface, JTAG, whatever. And then we tell the FPGA to initiate a reprogram of the fabric. So at that point, we've told the FPGA to basically rewrite itself. As that happens, usually also the host interface, like the PCI Express block, also gets overwritten. So the way we get around that today is we issue a PCI hot plug, pull the thing off the bus, and then wait for it to finish. And waiting is kind of like, I think it'll take about 30 seconds or whatever. And then we go ahead and rescan the bus. And then hopefully the device is back, it's powered on, and then we can go ahead and link train. The drivers get poked again, and we go through reinitialization. The big benefit here is that process can be like 30 seconds to a minute, depending on the chip, depending on the bit file size. The other way to do this is you put something into your flash and then you reboot your host. And then that process happens on boot. And on, like as anyone knows, on modern big systems with a lot of RAM, a reboot can take like 5 to 10 minutes. So practically speaking, in an environment where you have a lot of churn and a lot of change, rebooting is not an option. Unless it crashes during the reprogram, and then you have to reboot anyway. So why is that important? So in CXL 1.1, it's very explicitly stated in the spec that it does not support hot plug. That is, I think, very intentional because a lot of the focus has been on .mem out of the gate. You don't really think that you're going to be hot plugging your disk shelves or your memory shelves. So it wasn't very important. However, now that we have seen some life with CXL and we start going down this path of how do we work this into our ecosystem, without that hot plug support, we're kind of at a standstill, or we have some issues that we need to work through. So this was brought up at the software working group in the consortium a number of months ago. I brought it up, was told that this was an implementation problem, not a spec problem, and that I should go talk to an implementation group. So that's why I'm here. But this did actually spawn some other questions from members in the consortium and other vendors that may have not realized, like putting the 2 and 2 together, that this was actually going to be an issue if they wanted to build a .io or a .cache device. That would need to be hot plugged. So Jonathan's point, and to Dan's point, there are some rumblings out of some of the vendors that the host side support the CPUs might be 1.1 plus, and they have still yet to define what plus means. And there has been some hints that limited hot plug support might be there, as in we might have a timeout period of a snoop to a device that we can go ahead and hot plug, and if we can get back in time before that snoop hits again, then we'll be fine. So there's a lot of hand waviness and a lot of loose requirements here. But the whole point here is that's great to know, but between 1.1 and 2.0, I think it's going to be a bit of a bumpy mess with, like, say, Intel has one 1.1 implementation and AMD has another 1.1 implementation. And it's going to put a lot of pressure on endpoint developers and designers and software developers to accommodate for all of these little quirks. So I hope that that's not the case, but we're already kind of seeing it a little bit right now. So Proposal. I have two ideas. I don't know how anyone will take either of them. One of them would be on the kernel side to expose a best effort hot plug hook and say you can go ahead and try to do what we do in PCI Express today and hot plug it and rescan it, and it may not work, and put on, like, you know, use at your own risk, use at your own peril, but at least it would be something that, given some of the quirks on the host side CPUs, we might be able to make this work. Obviously, some thoughts that came to mind for me is CXL.cache could be tricky because that's effectively doing a CPU hot plug, more or less, if you are actually participating in the cache coherency. And mem would be a little bit tricky, and this was actually brought up yesterday in the meta presentation about how we would have to quiesce any transactions before we make any changes. That all makes sense. That can all be handled in software. So this is one thought. The other thought, and this is actually pushing the responsibility onto the FPGA designers, and that's why I don't think this is actually going to fly, because I've been told by my FPGA designers this is not going to fly. But we could implement partial reconfiguration. So this is another method of building your bit file that goes onto an FPGA where you actually have segregated out parts of the IP, not necessarily having hardened IP like in a PCIe core, but you could have a soft PCIe core that's fully separate from the area that you actually program. I think some of the Intel FPGAs have this as part of their HLS environment, but it is something that would be a major change to how people architect their bit files. And if it's only the stopgap to get in between today and 2.0, it may not be something that people look as worthwhile to spend the time on. So this is one option. I did feel like I needed to be honest and put it out there that we could actually work around this without worrying about like a use at your own risk kernel hook. But obviously this is not the most ideal. And with that, I said it was going to be shorter and give you a use case, and then people can start firing questions and terrify me.
So it's good. That's good targeting question. So I have some comments on this. So I'm Jonathan from Facebook. Meta, we changed the name. So a difficulty with CXL.main support for hot plug is that memory is part of the critical computing infrastructure. So the host processor has to deal with cleansing the memory stuff and the flushing things out and make sure apps also deal with correctly. But in this case, you don't have this problem because you are only CXL.cache. Now, when it is CXL.cache, that means there are caches in the CXL device that could cache the memory from the processor, right? So if the processor has the latest data, cache data, you unplug the device, doesn't matter, who cares, right? Now the problem is only when the cache in the processor side is stale, but the cache in the IO, in the device side has the newest data. Then you unplug, if you don't do anything, the data is gone, right? So if we just make sure that doesn't happen, then we are actually good.
Yeah, no, I agree. I think
how to make that happen? One is that from the usage side, you can say, oh, if you are just doing firmware upgrade. So in that case, you can, when you finish the firmware upgrade, you can invalidate your cache on the device side. That's something device can do before you do the hot plug. Right? So that would be my suggestion. Another thing about you said about the CSFS stuff, maybe you can, I don't know much about the BPF, but you could use that for your own purpose. Because you won't be able to get that into a production system. Right? And you know it's not for production system, it's for developers' efficiency. In that case, why not just use your own patch or use BPF?
So the hot plug actually in this case is something that we use in production quite often. Say again?
I see. So that's my misunderstanding. So in your case, you want to use it in production.
Yes.
So if you want to use in production, then you have full control of FPGA. Then you can avoid the situation I was talking about, where device has the latest cache.
Yeah. So if we do have something like a device biased cache or device biased memory, having the FPGA and any of the software around it guarantee, or at least do its best effort to make sure all of that's flushed and invalidated is a perfectly reasonable assumption to make sure that that device does that. But the piece that we need then is the kernel side to be able to support the hot plug after we've gotten all of that flushed out.
Yeah, I think, yeah, as you said, right, PCI also have the infrastructure where, like, for example, you have the PCIe uncorrectable error handling.
Yep.
You have the EDPC, enhanced. I forgot the 14, but basically, yeah. Thank you. Enhance the downstream port containment, right? So basically means if there's a uncorrectable error happened, it actually take care of the aftermath dealing correctly, and then reset, reinitialize the link, and then rescan and re-add it to the stuff. So all I'm saying is those today it needs some firmware support, need some SMI handlers. But all I'm saying is the technology is already there. We just need to make sure it also supports CXL. That's it. I don't think that should be a lot of work. But make sure your firmware already supports it.
Well, and this was also more of a, if we were to start pushing patches to kind of put these together, would people be screaming into the night that this is a terrible idea? And it sounds like probably not. So.
Kernel upstream always has this, right? So that's good. We debate.
Just from a practical point of view, if you're dealing with a Type 1 device, as far as I can remember, there is absolutely nothing guaranteeing the host won't issue a snoop. Doesn't matter if you've even had the address, it could have lost tracking. In which case, there's nothing CXL can do or software. So, I mean, there may well be, the way of these things, there's probably somewhere in those hosts a register somewhere that will let you turn that off. We could look at defining something like a firmware interface to actually expose that if the host had it, thus allowing the host to hide away its magic chicken bits. But I can't see any other way we can solve that problem.
Yes, that is.
I mean, unless you actually, to be honest, even a host, yeah, even if you told the host it had gone away, DPC is, yeah, interesting with 6L1 devices.
I mean, if it was able to catch the NMI that was coming and we could reset the device that way and kind of get a cheap for free hot plug. I don't know. That's something to look into.
I think you need the FPGA to guarantee to return a miss under all circumstances if it's not booted, etc. Which means some hard IP, or it means, yeah, partial reconfigurability. Otherwise, good luck.
Yeah, thank you. Yeah. No, I think having some of those restrictions on the FPGA is perfectly reasonable for what we're trying to do.
We had a vote online, by the way, and we've decided that reconfigurability is the right solution and we should do nothing at all in the kernel. It's on the chat. Strangely, there are no FPGA types here today. Yeah, there are only 2 votes.
Yeah, I just want to point out, you're fine pushing that upstream, I think, because like people know upstream that if you're doing outplug, it's your mess, and there's very low expectation of it working. So
fair enough. It's the bed that we made.
So I missed the beginning premise of this, where the fact that the link is down causes those snoops to be a miss. That's why you're trying to get to hot plug.
Yes.
Would the same thing happen?
Timeout. The assumption is you wouldn't, yeah, ideally the host wouldn't be sending snoops anywhere near something where the link's down. Guarantees will be host specific.
Isn't that the fundamental thing here? Like when you say that it's like CPU hot removal, like a removal, right? It is, but it's at the same time, is the OS aware of that compute resource on the device? Isn't that the more important? Like, who was the one that initiated the compute on the device, and can they stop it and guarantee that it's not using it anymore? Like, does it boil down to this at all, or?
Well, there's really, maybe that was a little bit of a much hand-wavier statement. So that's not assuming that you might have a CPU on the device that is also contributing or participating in the cache coherency with the host CPU. It could just be that the device itself is placing stuff in the cache on the host. So it could be tracking cache lines, but it doesn't necessarily mean that it actually has a caching entity on the device. If it did, that would be way harder to deal with, because then yeah, you would have to do like all of the invalidates, flush them, go ahead and disconnect the compute resources and rip it out.
A characteristics of the CXL caching mechanism is actually asynchronous. So what that means is the processor is the master and device is slave. The processor has the daunting job of making sure the caching MESI operation is correct. Today, the Intel Sapphire Rapids and AMD Genova went through a lot of work. We work with them for a long time, so they're pretty good.
Yeah, we've kicked the tires as well.
Yeah.
Speak.
I guess thank you for the
Yeah, thank you for your time.
Hello, my name is Robert Richter. This talk will be about CXL error reporting. It has created together with Yasin, who joined online probably. This is a short overview of the presentation here. I will give a brief overview on the CXL design with respect to impact on RAS and error reporting. I will especially talk about CXL memory devices and then go deeper into the error handling here, where I will also briefly touch the RCD mode, which is the restricted mode introduced basically with 1.1, and the impact on error handling, and then an outlook on kernel implementation and also userland. So in the end, I hope there's some room for discussion. So how does a CXL system look like? We have basically additional to existing DRAM in the system, there's now a CXL memory device plugged in to the same system, similar to PCI. This is shared through this through a link here, a CXL link, and this enables us to include additional memory to the system through a standardized interface. We have a way now to include memory with different characteristics, which can be optimized with respect to costs, capacity, power, etc. This memory resides on the device here, but it is managed and controlled by the host, which means that the memory itself is plugged in to the system's coherent address space. And as such, it is accessible through load store semantics to the system. I also want to mention that this device topology is visible in the PCI hierarchy to some degree. I will talk on this a little later. And this link here can be shared with PCI, so that you can also use this link to plug in PCI devices, and the devices then show up as PCI devices with PCI host. So how does all this impact RAS and the error detection on these devices? In a native system, we just have the DRAMs here and the CPU. There's a memory controller in the CPU typically, and that's it, no big deal. We can fetch the errors from there. With CXL, this is different. We have now a host. We have now a host here and a device where the memory is on. We don't have any longer a unique memory controller in the system. We have now more entities that can detect errors from system memory. The device can also report errors and provide also error details here. Once an error pops up here in the memory, in the device's memory, then this must go through the device, through the link, and to the host back. So many components are involved here to detect the error compared to the local system memory. And with more locations also, we see different error types in the system, which have a different error flow. And all this makes things more complex. Also, another note is that these devices here come from different vendors, so it's no longer a unique system from one vendor. So we have here different memory cards inserted, which might also have different characteristics or different implementations of the error reporting. What else has impact or affects the error reporting and RAS here? We also have firmware first and OS first. I will talk on this later in the details on the memory. We have this two CXL modes. The VH mode, virtual hierarchy, is current implementation basically, and there's the restricted mode. Both modes have different topologies, and this also causes a different error flow. Another thing is we see CXL memory the same as standard system memory. So we then will also have the expectation that we have the same look and feel with respect to error reporting here. So that raises the question how we integrate this into existing subsystems. But this might not fit well because of the changed way the errors are reported. We might need to implement new tools to detect the errors, or we might add the error handling part to existing tools like ND control also. And the next complexity here is also error injection itself. We have this many components involved and tools, and for each we might need different, for each kind of error type or component we might need different tools, different approaches how these errors can be injected. So where can errors happen in a CXL memory device here? You see here the host and the device that is connected through the flex bus, or basically a CXL link if there's a CXL link connected. Then we have these three components here, CXL RAS capabilities, PCI AER capabilities, and here down also the mailbox interface. For the CXL link, there are 3 CXL protocols we talk on. There's I/O, MEM, and cache, and these can be formed to 2 groups. So one is the I/O part, and the other is the cache MEM part. Depending on where the error happens, it can be either happen in the host or in the device. So we have 4 points where protocol and link errors can happen. One here for the cache mem part, host and device each, and here for the I/O part, also host and device each. And then there's the device error itself, or device-related errors itself here, which report memory or thermal errors on the device. And these are logged in the event log, and the mailbox is used here to read this out of the system. So based on this system design, we have 4 types of errors that can happen. The first 2 are poison and viral. These are basically integrated into the memory management of the CPU. Both are unrelated to CXL. We don't need additional drivers, so they have already solutions here, also from the handling point of the host. For poison, we tell the host that there's corrupted data with a data packet, and the host then has some host processor specific behavior, which could be marking this memory bad also, depending on what's happening. The only difference here is that we need to enable poisoning through mailbox command mechanisms, and then it's just enabled. Viral is slightly the same. Once an uncorrectable fatal error occurs on the device, for example, it can tell the host processor, and then there's also some host processor specific behavior, which means basically the system, or once such an error occurs, the system mostly cannot continue to work, and typically this leads to a system freeze or system resets, depending on the implementation. Now there are the CXL memory errors. We have these 2 types, the protocol errors and the component errors. I will go into more details in later slides. Basically, for protocol errors, we are using the PCI subsystem, the AER error reporting, and for component errors, we have a mailbox that can be used to read the error log or event log. So protocol errors, there are these 2 differences between firmware first and OS first. In the firmware first case, the firmware just consumes the error, and it may then signal to the OS and using existing ACPI methods, further the error that happened. For this, the CPRO error format was extended in last UFI specification to also represent CXL protocol and device errors also. So these are then typically sent through a GHAS interface back to the host, the OS. In the OS first case, the OS must handle the AER events using the PCI subsystem. If there is an internal error, then the OS needs also to examine the CXL Rust structures here. And depending from where the error was detected, either the downstream port or the upstream ports needs to be checked for errors. For components errors, we have, or we need a CXL driver, which basically has two parts, or serves two parts here. One is to access the event log down here with some sort of event handler, and the other is to maintain or to control the mailbox interface to read out this error, basically. So once the driver is initialized, the driver must first take control of the memory error reporting here. It's using the ACPI OSC method, which means that the OS must request that it further wants to report errors, and then the firmware needs to grant this request. And then it can continue and basically looks into the event log. If there's an event pending or so, then the mailbox interface is used to fetch the errors from there. The event driver then further parses the error records and reports them further, and may also have some further actions to report this to the operating system. Yeah, that can have further actions on the error. Some notes on the differences between VH mode and restricted CXL mode. This is the software view of a VH of a VH case, and basically the most interesting part is this one here in the middle. This is the part where no restricted CXL device is included, and we see here the root port. We have a switch in between here with a downstream port and an upstream port here, and this one is then connected to the endpoint. All these components are visible in the PCI hierarchy, and we can use PCI access methods to access the components of every component here, the structures of every component here, either in the root port or the down or upstream ports, or also the endpoint. And this means there's basically a way to access, easy to access with existing methods, the PCI structures that handle the AR errors. If restricted host, this is different. You see here one node here to the restricted CXL devices. Once the device is in the system, another restricted CXL host is created, which forms a pair. So same as here for this device, which was originally attached to this switch. So we have always a host device pair available in the case the device only supports restricted CXL mode. And another node also, here you see the PCI link shown up, which means that here's a PCI device connected to. So the same CXL node can also be used as PCI device. Some more details on restricted CXL device mode. This shows the diagram how this is seen in the system. We have a restricted host here with a downstream port, and here's the restricted CXL device, or RCD, which also has a upstream port here, which is not visible in this image, but it also exists. Now in CXL RCD mode, which is the former 1.1 mode, we don't see this downstream and upstream ports here. So these are not part of the PCIe hierarchy. Also, the device shows up as an root complex integrated endpoint. And that's why we have also an event collector here, an RCEC, who's now responsible to propagate the AR errors. To access the downstream and upstream ports, there's an additional root complex register block, which resides somewhere in the memory mapped ranges. And this needs to be mapped separately to get access to the downstream and upstream ports. And this register block basically shows up with PCI type 1 or type 0 header, similar to PCI. And therein is also a link into the component register set. Component register set contains the CXL RAS capability structure to read out the CXL protocol errors. So this is the same here, but it needs to be handled differently once an error is detected here in the RCEC. So what is in the kernel missing all of this? So where's the RCD? So RCD mode is missing. I sent a patch series 2 weeks ago here on this. We also need a CPER extension of the CXL protocol errors. I think there was a submission already on the mailing list. Then the AR handling needs to be, of a PCI subsystem needs to be modified in 2 ways. One is to make use of the CXL RAS capability structures. In case an internal was detected of an CXL device or host. And then we also need to add AR support for RCD devices, RCD mode devices, which means that we need to detect the messages coming from an RCEC. This is a CXL device. We need to extract the downstream and upstream ports that are in separate memory ranges. And for this all, we need to extend the PCI infrastructure in the kernel. When what is also missing in the kernel is the interrupt support. We need this as well, and there's also no event driver at the moment. It must not necessarily be a separate driver, but we can also extend, for example, the CXL mem driver in the kernel already. And then the next question here is how we can extend existing subsystems. Do we have, we need to extend the kernel logs. We might want to attach the error reports to trace points, or maybe also we extend the EDAX subsystem, which gives us the next question on how we...
Sorry, can I just ask a quick question? Just a clarification on the previous slide. The CPER record,
yes.
Is there an OSC to negotiate if the OS has any idea what that is?
Pardon?
Is there an OSC? As in, can the firmware query the OS to ask whether it's understood, or does it need to do, well, it's chained CPER records? Because if we have an unaware OS, which they should all work, well, okay. If you're doing
I think
firmware
it's just
code,
an extension of the bitmap of the kind of error that happens. So
OSC already extended to support this.
Okay, cool.
Yeah, this handshake.
The next slide was about user space here. So many things could be moved out to user space, which includes which could include also mailbox interaction monitoring tools, event handlers. There might be a need for address translation to to have a translation between device addresses and physical system addresses, which might not be trivial. And fault analysis and interleaving region setup could be also moved out. But the general question is how what's the kernel user interface? How simple we want to have kernel drivers here, and how this could be look like. But to some degree, the kernel should handle the errors also and be aware of at least fatal errors. So to summarize all this, we have this CXL way to add a flexible way to add system to the memory for to have the same look and feel as for native memory we want to have, or we need RAS here also as a solution. But there are many components involved with a variety of errors that can happen. Some of this is already available in the kernel, machine check exceptions, for example, and parts of the PCI error reporting that can be reused. But the CXL protocol and component error implementation, this is completely new, and we need new patches and kernels for this. And I hope we can also contribute a little here in this area. So that's the end of my presentation. I would like to thank you, and I hope there's some room for discussion also, or some questions. Sorry. So references are CXL specification version. Pardon?
Yes, it's public.
It's public, yes.
So, does this work?
Yeah.
At least with regards to the mailbox interrupt stuff, like this is more of a like kernel, like more less CXL and more like where we are with the kernel. I also want mailbox interrupts. And right now the caveat is basically like dynamically allocating vectors for the DOE. But I'm wondering if we can, for the users that want interrupt support that don't have that problem, can we just have a basic MSI, MSIX implementation and just go from there?
I'll take that one, if you don't mind. Okay, so the interrupt situation today is ideally we'd like dynamic resizing of the MSIs allocated so that along come various things and various different bits of the driver, and they all want an MSI, and they can all request it, and we just keep sizing the thing up. Unfortunately, kernel doesn't yet support that. There's been some discussion of it, but it hasn't happened. But what we can do is the equivalent of what the PCI port stuff does for the switches, where you basically have a whole load of pre-registration things where there's little bits of code for all of the features that might be there that go snooping around in all sorts of config space and various other places, figure out the largest MSI number, and then just allocate the thing. Yeah. So that's what we've got in it was in the, as you say, the DOE stuff before. And I mean, my personal feeling on that is we just take it with the first user. What we haven't yet done is accept any of the users. So it's been in several patch sets.
One like simple solution to like that crossed my mind, but it's obviously not usable. But like just allocate an obscene amount of vectors. And yeah, that's why.
Yeah, don't do that.
Yeah.
There's just one thing I would like to see all the parsing and log handling to be user space. People like me will not do log error handling in band for CXL. We do everything out of band for various reasons. So anything that will be inside the Linux kernel will be useless to me. But obviously you need stuff in the Linux kernel, and I'm fine with that. But all the parsing, handling, and so on of the log you get from the device is something I wish as user space, so they can be reused by other people.
If it's a memory error, you've got to handle it in kernel.
Like you got the poison. That's it.
No, well, okay.
Yeah, you get the poison. I don't need anything else. That's fine. I won't be doing anything in Ben. I cannot. Actually,
so you
I
do nothing
technically
preemptive.
cannot do anything in Ben.
Okay, so you do nothing preemptive if you get a memory error. So normally, the first thing you do if you get a memory error like that from a RAM scrubber, what do you do for DDR RAM scrubbing?
So symbiotically, I'm talking about here, like you have to think, like in my case, it's experimental. I don't know who is running the operating system. I don't know what the operating system knows. I don't know what it is. So it's like, can't do anything. It's not my problem. But I need to be able to get the error log out of man.
Yes, you don't even tell them that the memory is corrupt?
So they're going to get the poison. So I assume by default, if they have a basic operating system, they're going to get the poison. The poison is going to be beyond the CPU. The CPU is going to get EDAC. EDAC, you're going to put page poison and so on. So you're going to go machine check exception and so on. So it's going to be fine on their front. But on my side, I still want to know about the error.
So I understand what you're saying. So it makes sense to me, but that's an implementation choice. No, customer use choice, right? Data center choice, policy choice. So different data center would have different strategies. But CXL spec supposes this. So what happens is you have two mailboxes. The device is required to have two mailboxes. So it's designed that firmware, let's say in this case, could be out of band, and the host use different mailboxes. So the device could say, hey, send the correctable errors to one mailbox for OOB to consume, and uncorrectable error to the other mailbox for this kernel and OS.
Yeah, it's like somebody can correct me, but like it's just the primary mailbox that we currently
there
have.
are two. That's two sets of mailbox.
Yeah, unfortunately not. It's optional.
The secondary.
Secondary one's optional. There's no guarantee it's there. And to be honest, the use model around that is horrendous for any guarantees that someone isn't already using it. So it was put there for that purpose. It's not easy.
Also, the design is that the kernel driver will do the direct interaction with device, nobody else, for the primary mailbox. So that once it gets it, you can choose not to deal with it. Then it goes silent, and then OOB takes care of it.
Okay, let's thank the speaker.
Thank you.
Next one is Jonathan.
What my own presentation's called. I was pleased to see Ben was online. So if you have any questions about this stuff, ask Ben. As I'll come on to it, he originated this particular piece of work, and I've taken it over in more recent times. Okay, so the purpose of this, which is the last session. So everyone wants to leave early, so no questions, and we'll get out here quickly. But yeah, do jump in at any time with any questions. My basic aim here is to give some quick update on where we are today. Quite a lot of that is what do we have implemented but not upstream, where the focus is, that sort of side of things. Also, trying to explore things that people actually want. I mean, what are you missing for stuff that you actually want to test? Kernel development side of things, as I'll come on to it, relies somewhat on QEMU. I wouldn't say it relies on it, but we found a lot of bugs. So it's proved certainly useful, and the early kernel development did indeed rely on QEMU because there wasn't anything else. Okay, already said that. Okay, so very quickly, why do we care about QEMU emulation of CXL at all, or indeed QEMU emulation of anything? Ben did a particularly good introduction to this in the talk that he did at Plumbers last year. So if you want lots of detail on that topic and some discussion around it, go look at that. But the key thing here is it allows us a platform to do flexible emulation of really quite complex configurations. We more or less, via a command line interface, can emulate anything. Okay, we're still missing some stuff, but we're building up to that fairly quickly. And we'll come on to what is supported today a little bit later in the talk. We can poke all the paths. It looks like a real PCI system. All of the sort of flows are actually going through all the different layers of emulating different components and emulating all of the code paths. Well, okay, sorry, requiring all of the code paths in the kernel to hit those. So it turns up stuff that isn't there in the thing that was mentioned earlier, which is in tools, tests, I think in the kernel. There is a CXL mocking interface that allows you to do a lot. And the work that Dan and team have done on that has been so very useful for making sure the kernel code does what we think it does. There's a different purpose, basically, for the QEMU code. It's something we haven't done yet, but one of the things I definitely want it for is testing and continuous integration. So over time, I want to get this into some of the test farms, mainly because even when we do have lots of CXL hardware, we're still not going to, generally in the test farm, have all of the different configurations. There are insanely large numbers of different types of interleave, different setups that you can have. We're only going to have a subset. If we can emulate a few more of them and hit a few more of those corner cases, that would be great.
Quick thing, you should talk to Luis about KDevOps, testing framework, and he was asking me about reasonable configurations of CXL topologies put into an automated framework, and like the exact question, you should chat with him.
Excellent, thanks. I will do. So, my dream. My dream is that the CXL QEMU emulation will be sufficient to exercise absolutely everything that we've got in the OS side of things. Until I've got some software to poke it with, well, there's not a huge amount of point in emulating it. And basically, yeah, just testing everything. As I'm dreaming, I'd like to do fabric management as well. We'll come on to that a little bit later. But getting to the point where, and it's been discussed earlier in this, the fact we might have a nice open source fabric management layer or even orchestrator, providing a platform on which to both test that and use it to drive testing of the different topologies and make sure that the host does the right thing when it's passed the right configurations. One thing that we have found this useful for, and I can't go into a huge amount of details, is using it for specification prove out. So before the specification is released, if we have a reasonable, sorry, put that off, a reasonable baseline, we can fairly quickly implement things that are being proposed for the spec. And this leads to us fixing things that would otherwise turn up either as errata or horrendous workarounds. So this has already been useful. The PMU RFC that came out very soon after the CXL 3 spec was largely because we'd used it for spec prove out in advance and had indeed modified various bits of the spec when we discovered things that didn't work so well or weren't tightly enough defined. It's very helpful to have an implementation. So there's a trade-off here. In order to test a feature in the kernel, what we need is a proof of concept. We need to be able to poke it. Well, it doesn't have to be clean. It doesn't matter if we're hacking through various layers of QEMU to get to the right places. Yeah, it's much like any other proof of concept. A number of these have been sent out as RFCs. Myself and I think a few others have also sent some of these. It's good enough for that purpose. The problem we have is that works today for adding one feature, but then when we build some other feature on top of it, we've got a steadily growing unmaintainable mess. So hence, upstreaming is good, even though we don't technically need it to verify a particular kernel feature. I'm sure plenty of you have interacted with silicon verification teams, and it is kind of the difference from the scripts they write in order to say, does this thing work under this very narrow set of circumstances, and the equivalent of having a software stack that's actually going to get used. So that sort of refinement, both are useful, slightly different purposes. So, progress report. What have we actually got upstream? So there was a QEMU release a couple of weeks ago now. We got quite a lot went in. So we have CFMWS, which is the host physical address window stuff, and all of the associated description to the OS. We have host bridges, which are done using sort of extension of what was the PCI expander bridge, which exists in QEMU and doesn't represent any real hardware at all. It's mostly traditionally used for things like representing NUMA topology of devices to QEMU virtual machines. But rather helpfully, it had a nice sort of general implementation of a host bridge to which you can attach root ports. So, yep, we've got 6L root ports, we've got switches, and we've got type 3 devices. We haven't got any type 1 devices. So some of the flows we've been talking about earlier, we have no way of testing them. And we don't have anything that is capable of, well, okay, it's QEMU, so anything that claims to be capable of caching. So if we want to explore some of those things, that's something we could add later. We have everything very, very nearly needed to bring up interleaved persistent memory on type 3 devices. So you can do all sorts of things. You can do direct attached type 3 devices plugged into a root port. You can do a switch in the path. You can interleave across multiple host bridges. So basically everywhere the spec allows us to do interleave, we support. It's fairly simplistic. The devices, and in fact, everywhere down the path other than at the host bridge level, only have one HDM decoder. It's enough to test those paths, but if we want to carry on and allow for more complicated things where you're interleaving from one device in multiple different sets, that sort of stuff, we obviously need to extend that, but it works for now. The star there is because quite late in the development of the region patch set was added the sufficient to get to the point of actually creating labels, and those include the serial number. And that is the world's smallest patch. It's like 4 lines of code, absolutely standard QEMU stuff, wasn't there. So the reality is, while you can bring up an interleaved persistent memory set, you can only do it once. After that, you have to create a new one because there's no provision for a sensible label. But yeah, that patch is tiny, and we'll get that upstream fairly soon. So other things that are done, but not upstream. ARM support, which I care about because I work on ARM servers. That's blocked by a QEMU issue, which is that they prefer for the ARM machines, or for ARMvert at least, where we were using it, to always have device tree support. And that's a sort of historical thing about where their main use cases are. And that means that if we want to do that, we've got to provide the provision in the kernel for, instead of using ACPI for the root device, we need to provide device tree. It's not a big job. It's not particularly useful for anything other than QEMU upstreaming. For now, I'm sure there will be embedded hosts of CXL devices at some point. But at this stage, it's kind of on the list to do when things get really boring. But it would be nice to do, because then we have a second architecture and can hopefully highlight any small things that aren't there. I mean, there's one thing going on in the kernel at the moment around global flushes. I mean, simply enabling that thing would allow us to go, oh, that function isn't there. I mean, we've noticed anyway, but nonetheless, it is useful to have more than one architecture. DOE and CDAT support is been around actually quite a long time. That was done by some of the folk at Every Design. The main thing I've stalled that on is the original design relied on you hand creating or using some tooling to create a CDAT table, then sticking it in as a file. Given that we have a nice configuration interface for defining all sorts of different types of device, it would be nice to automatically generate something that is plausible for whatever it is. So trying to fill that gap, which again is not a particularly big job, but has not yet been done, so I haven't attempted to upstream that. DOE compliance, so the compliance interfaces. Does anyone want them? I mean, from an OS point of view, we don't really. I mean, it's test suite type stuff. They're not particularly invasive. The implementation that's there is pretty much a stub. It'll sort of say, yes, everything works. But if anyone does want to develop more on that, do let me know. It's not one I'm going to focus on. The PMU stuff from CXL3. So this was written, as I mentioned, to do a bit of spec prove out, and was the kernel driver that goes with it. Both have been posted as an RFC. The QEMU stuff is nowhere near controllable at the moment. It's a hard-coded, entirely random set of events that are counted a bit strangely, but it does give you enough to exercise the kernel driver. So this is one of those cases where there's a question of just how flexible a configuration do we want for PMUs in an emulated device? Or do we just want something kind of plausible that might represent what would be there? I mean, there is slight fun around that because the CPMU definition is extremely flexible. And there are quite a few interesting corner cases where you have particular combinations of fixed and configurable counters and this sort of stuff that can come in orders that require you to do a bit of searching and removal of things from lists and that sort of thing. So trying to come up with pathological cases that will at least exercise what's going on in the kernel side of things is probably worthwhile, even if they were something you never build. Yeah, we say that today, but someone will build it. Switch CCI mailbox. So FM API's been mentioned briefly as the sort of thing that's out of the OS control. CXL3 added the ability to access via the switch all of that infrastructure. The intent for this actually is that mostly what you'd be looking at is a BMC using a separate PCI connection, a separate upstream port on the switch to access this. Or you might have a very simple system where for some reason you need complex switch configuration, but you're only using one host. People drew diagrams for it. I have no idea if anyone will build it. But from a testing point of view, it allows us to do nice closed loop stuff because we can then control what the configuration, the runtime configuration of the CXL devices is from within the host OS. It's fairly straightforward. I think this is a sensible thing to implement. And yeah, as I say, it gives us access to that. And crucially, it then would allow us to do things like dynamic capacity. I think, as I mentioned earlier, we need some emulation for. We had a birds of a feather on SPDM yesterday, and I think we have a path forward for the kernel side of things. All of that work has been done against QEMU emulation of just enough to pass through via a socket to, it's a test program that DMTF have called SPDM-MU, that uses libSPDM, and that provides the infrastructure to actually test that stuff. It's handy. Poison injection. Yeah, this was something that was incredibly easy just to add when the kernel patches were posted for this a while ago. So we popped it in just to check that the kernel side of things worked. But this is very much a hack. If we want to do poison injection properly, we need to do a whole load of tracking, and we actually need to return poison when someone does a read. Not totally clear to me what poison looks like in QEMU. I don't think it's a concept that's actually there today. At the moment, this doesn't do that at all. It injects it into the list of things that you read back. If you actually read the memory address, you wouldn't see anything at all. So there's potentially stuff around there that will come in handy for some of the RAS testing. Again, if anyone wants to take any of these things on, what I'm looking for is, yeah, more contributions. So I also listed at the end here stuff that's turned up on the kernel mailing list that we haven't got at all in QEMU today. Event logs, a particularly major thing to add to QEMU. It's not that complicated. There's a whole bunch of structures to be defined, but, or sorry, defined. They need to be typed in from the spec, but it's not tricky. The security commands, that's been a fairly hot topic on the mailing list and exactly how those are handled. Again, the QEMU side of things is pretty straightforward for those. Depends on just how much we want to emulate it. We could just emulate the interface and not worry too much that nothing actually happens on the device or the emulation of the device. So if you were to read it during that phase, you'd carry on getting the memory that you're not supposed to be able to. Or we can put some really basic gating in the way and return garbage. 6L 1.1 support. So this is obviously of interest to some people in the room, given the other talks. We can do it if someone wants to. It's not something I'm particularly focusing on, at least partly because there are hardware platforms available for that. But again, if it's useful, particularly perhaps for driving some CI type situations, it's not a tricky thing to do. Although, yes, the mention earlier of EDK2 support, one thing about CXL 1.1 is to exercise a lot of that stuff, we probably need an open source firmware as well. So looking at some of the stuff from that talk may provide us with some useful components to build that. And I listed a few fun things that I haven't looked at at all. Don't think anyone else has. Okay, so the first one should be really straightforward, but we never really bothered because it wasn't something the kernel stack was really doing anything with yet. I know from Dan's slides from the other day, from the sync call, that the plan is to get volatile capacity support into the kernel side of things fairly soon. So yeah, we'll want to add it to the QEMU emulation as well. Along with that thing I mentioned earlier about there only being one HDM decoder. Obviously, if we've got both persistent and volatile on a device, we're going to want at least two HDM decoders. And obviously 2 is near infinity, so we'll go with quite a few when we bother to implement it. Yep, dynamic capacity, the stuff we were talking about earlier. I think that's tricky enough to work out what we're doing on the kernel side of things that we definitely want a platform to poke. Thankfully, yeah, the kernel stuff's hard, but the basics of actually wiring it up, and an incredibly inefficient implementation at least in QEMU is not tricky at all. It's just, we already have to implement all the interleave stuff. It's just another address check. Is this one here or not? If not, go away. However, it does need the FM API side of things. From that point of view, we're going to have to use a switch front end with a mailbox, and then we're going to have to tunnel the commands down to the MLDs on the actual device, which we're presenting the dynamic capacity on. Not that tricky, but we haven't done it yet. Yep. Oh yes, for fun, this one got mentioned earlier about shared memory and the entertainment that can be had when you share the memory on a single CXL device to 2 different root ports on the same host, so it appears aliased. Actually, for testing all of this dynamic capacity stuff, the presenting it on different root ports of the host, maybe not shared is a bit too weird, but in all other cases, the easiest way to do it is to have it removed from one port and appear on the other port, because it gives you a very easy way to check silly things like all of the correct clearing commands have been sent as necessary, because yeah, memory turns up over there, has it got anything in it? Or if you want to have something in it because you're doing that virtual machine case that was asked about earlier, then yeah, I mean, to be honest, virtual machines migrating from port 1 to port 2 is probably not that helpful, but nonetheless, we can use it to test the software stack around that. Fabric, this got mentioned in the security talk from Jerome. The complexity that CXL3 introduces around this is large. For now, the problem is that not all of the interfaces are actually designed. There's some to-dos in the CXL3 spec. So once that stuff materializes, then we'll want probably to emulate enough that we can poke the host side of things. I'm not sure it would ever make any sense to emulate the full complexity, but we'll see. If we're using something like the QEMU thing to help develop the FM API controls, then we'll want to emulate enough that we can poke the corners of that software stack. Oh, getting towards the end. What we need, more review. So yeah, review is always a problem. The issue here is actually we've had great support from the QEMU community around this, but none of them know anything about CXL. As you might imagine, it's still a little bit specialist. Hopefully they're learning, but it would be very helpful to get review of, frankly, just the CXL parts. The silly things like, are the registers defined correctly? You know, the stuff that is boring to review, but not particularly tricky. You just eyeballing the spec and making sure it's all right. So that at least we can then say to the QEMU folk, from a CXL point of view, this is correct. And then they can focus on the QEMU interfacing and the more specific parts of it. More features. So I've listed a few features that are on the list of things I'd like to have. And there are a host of other things in CXL2 and even more in CXL3 that we haven't really got to yet. So if people have particular things that are of interest to them, or indeed the CXL 1.1 side of things, then yeah, please step up and send code. I'm certainly happy to talk to anyone about approaches for how to implement anything. So my sort of final question around this is, having heard that quick summary of where we are, does anyone have a particular focus topic? Because I'll be honest, I'll work down it at the moment in the order that makes most sense for me, but my end goal is to get the kernel support for everything around memory, at least, upstream, all of the features around that. So obviously trying to synchronize things with what other people require should speed that up. So if you're working on a kernel patch and there's no emulation, worth letting me know in advance so that we can hopefully land them both at the same time.
So I had some patches for the volatile capacity aspects, which, as you say, it's very simple to implement. But and as we've also talked before, it's basically about like having the firmware like give you the HMAT distances and fabricating that sort of thing. So I never posted patches because the command line parameters were just insane. Like, and I just left it there. So I was hoping like if somebody can provide like some sort of EDK2 thing that we can use for that, and because that's pretty much the only difficult part in it.
But that one's an interesting one because so for CXL 1.1 level stuff, yeah, we need the firmware to be involved. For CXL 2, yeah, there is, do we say, I don't know, there's some recommendations out there that you still attempt to do it in the firmware because you may have an unaware OS and you try and build as much as possible there. There's nothing requiring it, and the moment we consider hot plug, you can't do it anyway. So from that side of things, that's kind of an OS problem.
Okay, then I guess I can post the patches.
That would be excellent.
Okay.
Thanks. One more slide, if I remember. Crucial slide. Yeah, go for it.
Thank you, sir. In your slides earlier, you were talking about what's upstreamed and what's not. Is the not upstream repository public, or what did you mean by that?
With one exception, yes. I haven't pushed the CCI mailbox stuff out because I was working on it last week and didn't get quite far enough. But the rest of it is, some of it's on the mailing list, the vast majority of it. But yes, I've got a slightly old branch pushed out at the moment. I can, yeah, share the link to that.
Okay, yeah, I'll bug you offline.
Cool.
Thank you, sir.
I need to push a new version out. It's, again, one of those things that didn't happen last week. Oh, yeah, I forgot the crucial thanks slide to acknowledge some of the people who've been involved in getting this upstream and indeed writing it. So,
sorry, I have,
go
I have
ahead.
one more question. Regarding the QEMU work, this is not particularly focused on, it was not particularly focused on QEMU. I'm just more curious as to where do you see the integration with the driver and perf for the performance monitoring?
For the CPMU stuff,
yeah,
it's a perf driver, so it integrates like any other standard-ish PMU in the system.
Okay.
So I wasn't going to do it any other way. That's how all our perf devices work. I know that there are, shall we say, examples out there in the ecosystem that are not using the perf framework. This one most definitely does. It's feature-wise, as you asked about it, there's a bunch of stuff that's not there. I haven't bothered implementing fixed counters, for instance, largely because they're not much use for anything. So I don't know if people put them down, but for a perf type situation, a counter that rolls away on its own and has no ability to stop and start becomes not useless, but not as useful. I was hoping if I implement the configurable counters, everyone will go, well, that's the only thing that works. So all the hardware will come with configurable counters, but I think that might be optimistic. Okay, I'll just do the quick thanks. So as I said, Ben kicked all of this off. I think he's online, but thanks for that, Ben. Chris and Hu Cheng did the DOE CDAT stuff. That was a great help for driving some of the DOE development in the kernel. As far as I know, there isn't any other way of testing that stuff at the moment. Yep, Michael Sirkin, who actually took the patches, which is the vital step of looking through them in detail and then accepting them, and a whole bunch of QEMU maintainers who've come in with, and reviewers, sorry, who've come in with various questions, clarifications, complete design changes. But we got there. So thanks very much to everyone who was involved. Any questions online? In the room?
Yeah, I was gonna make a comment. This work is absolutely amazing. Yeah, thanks to Ben for starting it and Jonathan for carrying the torch and getting, but also getting it over the goal line, because it totally changes the calculus on kind of hardware testing. Because the concern was always that QEMU should be a faithful representation of emulation environment, but is it going to be a place where we can land like just test code? And I think you've kind of broken that down, and when things can start flowing in. So I'm wondering, now that we're over that hump, how can we get this into the kind of continuous integration flow that you talked about? I mean, so CXL test was like, hey, here's something that we can control the schedule of. QEMU is a little bit less of that, but it's just what's your sense for like how much the community is willing to take? Is it just a matter of review bandwidth, and we can kind of get on a cadence that's more predictable? Because yeah, the CXL test is great for the things that can be mocked, and for things that's not mockable, it's great to have QEMU. But like at the same time, there's like QEMU is hard. In my sense, it's difficult to do some of these topologies where you can just kind of throw them together in a mock environment. So like I still think those two things coexist, but this definitely changed the calculus to be much more QEMU focused going forward for the continuous integration aspect of it. What's your sense on kind of relying on that going forward?
Oh, apparently we're running 10 minutes late. So let's
sorry,
get that offline, but I agree entirely, Dan.
All right, thanks, speaker. Thanks, everyone.
Yes. Is there another one? Yes, yes, yeah.
you